Hello and welcome. Tonight we're going on a journey to the coldest corners of existence itself, where the laws of physics reach their absolute limit and where even the atoms themselves fall silent. Imagine a place so cold that motion itself ceases, a temperature so extreme that molecules stop vibrating, electrons halt their dance, and time itself seems to freeze. This isn't science fiction. It's called absolute zero, and it represents the theoretical limit of coldness in our universe. But here's what makes it truly fascinating. We can calculate it, we can approach it, but we can never ever reach it. And tonight you're going to understand why that impossibility tells us something profound about the nature of reality itself. If this kind of cosmic mystery helps you unwind at the end of your day, consider subscribing. We explore the universe's deepest questions here, turning complex science into stories that help you drift peacefully into sleep. And if you enjoy tonight's journey, helps others discover these cosmic bedtime tales too. Let's begin with a simple question that haunted scientists for centuries. What happens when you remove all the heat from something? Not just make it cold, but remove every last quantum of thermal energy. To understand this, we need to travel back to a freezing laboratory in Scotland, where a man named William Thomson was about to change how we think about temperature forever. The year was 1848, and Thomson, who would later become Lord Kelvin, was pondering a curious problem. Scientists of his era used different temperature scales: Fahrenheit, Celsius, Réaumur. Each was arbitrary based on convenient reference points like the freezing and boiling points of water. But Thomson realized something profound: there had to be a bottom to the temperature scale, a point beyond which you simply couldn't go any colder. His reasoning was elegant. Temperature, he understood, was really just a measure of molecular motion. In a hot object, molecules vibrate frantically, bouncing off each other in chaotic patterns. In a cold object, that motion slows down. So, what happens? Thomson wondered when that motion stops entirely, when every last vibration ceases. That point, he calculated, would occur at minus 273.15 degrees Celsius. He called it absolute zero, and he created a new temperature scale, now known as the Kelvin scale, where this point was marked as 0 degrees. But here's where most people misunderstand absolute zero, and it's a mistake that even some science communicators make. Absolute zero isn't just really, really cold. It's not simply the coldest temperature we've measured or the coldest place in the universe. It's a fundamental boundary of physics itself, as unreachable as the speed of light. And understanding why it's unreachable tells us something beautiful about the quantum nature of our universe. Let me explain what I mean. When Thomson first proposed absolute zero, he imagined it as the point where all molecular motion stops. Complete stillness, perfect calm. But then quantum mechanics came along and revealed something unexpected. Even at absolute zero, particles can't be completely still. There's something called zero-point energy, a quantum jitter that exists even in the absence of all thermal energy. It's as if the universe has a built-in restlessness that can never be completely eliminated. This isn't just theoretical speculation. We know this is true because of something called the Heisenberg uncertainty principle. This principle tells us that you cannot simultaneously know both the exact position and the exact momentum of a particle. If a particle were completely at rest, at absolute zero, you would know both its position perfectly zero and its momentum also zero. The universe doesn't allow this. There must always be some residual motion, some fundamental uncertainty. Think about that for a moment. Even in the coldest possible state, at the very edge of what temperature means, the universe maintains a kind of quantum aliveness. Nothing can ever be truly, completely still. There's something almost poetic about that, isn't there? Even at the limit of coldness, existence refuses absolute stillness. Now, let's talk about the race to reach absolute zero, because this is where human ambition and physical law collide in fascinating ways. After Lord Kelvin proposed his theoretical limit, Scientists became obsessed with getting as close to it as possible. It became one of the great scientific challenges of the late 19th and early 20th centuries. The first major breakthrough came from a Scottish scientist named James Dewar in 1898. Dewar invented the vacuum flask, what we now call a thermos bottle, specifically to keep liquefied gases cold. Using this technology, he successfully liquefied hydrogen, reaching a temperature of about 20 Kelvin, which is minus 253 degrees Celsius. This was astonishingly cold for the time. For context, the coldest natural temperature ever recorded on Earth is minus 89.2 degrees Celsius at Antarctica's Vostok Station. Dewar had created something more than 3 times colder than anywhere on our planet. But the real prize was helium. Helium, with its incredibly weak intermolecular forces, resisted every attempt at liquefaction. It became known as the permanent gas, the substance that couldn't be tamed. Then, in 1908, a Dutch physicist named Heike Kamerling's Onnes succeeded where others had failed. On July 10th in his laboratory at Leiden University, Onnes liquefied helium for the first time in human history, reaching 4.2 Kelvin. He was just over 4 degrees above absolute zero. Onnes described that moment with an almost spiritual reverence. After years of failed attempts, he watched the helium finally condense into a liquid shimmering in his apparatus like liquid starlight. He wrote in his journal that it was as if we had opened a door into a new world. And he was right. That achievement earned him the Nobel Prize and opened up entirely new fields of physics. But here's what makes the story even more remarkable. The closer you get to absolute zero, the exponentially harder it becomes to go further. It's not like cooling your refrigerator, where every degree requires roughly the same amount of energy. Near absolute zero, the third law of thermodynamics comes into play, stating that you cannot reach absolute zero through any finite number of processes. Each step closer requires more energy, more time, more sophisticated technology than the last. Think of it like trying to reach the horizon. You can walk toward it all day, but you'll never actually get there. The horizon keeps receding. Absolute zero does the same thing. Scientists have gotten incredibly close, achieving temperatures of just a few billionths of a degree above zero in modern laboratories. But that final gap remains unbridgeable. Let me give you a sense of just how close we've come. At MIT, researchers have cooled sodium atoms to 500 picokelvin. That's 0.00000000005 degrees above absolute zero. At CERN, scientists working with anti-hydrogen have reached temperatures around 0.5 nanokelvin. These are temperatures that don't exist anywhere naturally in the universe, not in the coldest nebula, not in the darkest void between galaxies. Humans have created the coldest places in the known cosmos, right here on Earth. But we still can't reach zero itself. And this isn't a limitation of our technology. This is the universe telling us something fundamental about the nature of reality. The third law isn't just a practical obstacle, it's a statement about the structure of existence itself. Now let's compare these laboratory achievements to the natural cold we find around us because the contrast is striking. The coldest naturally occurring temperature on Earth, as I mentioned, is minus 89.2 degrees Celsius, or about 184 Kelvin, recorded at Vostok Station in Antarctica in 1983. That's cold enough to freeze carbon dioxide, solid cold enough that exposed skin would freeze in seconds. But it's still a balmy tropical paradise compared to what we find in space. The average temperature of the universe itself, the cosmic microwave background radiation that fills all of space, is 2.7 Kelvin. That's minus 270.45 degrees Celsius. The entire universe sits just 2.7 degrees above absolute zero. Let that sink in for a moment. The baseline temperature of all existence is hovering just barely above the theoretical minimum. The universe in its natural state is almost as cold as it's physically possible to be. But here's something that might surprise you. Even though space is incredibly cold, it's not the coldest place in the universe. That honor goes to the Boomerang Nebula, a dying star system about 5,000 light years from Earth, where temperatures drop to just 1 degree above absolute zero. We'll explore that cosmic freezer in detail soon, but for now, just appreciate the irony. The coldest known natural place in the universe is warmer than what we've created in laboratories here on Earth. So, why does all this matter? Why should we care about absolute zero beyond scientific curiosity? Because understanding absolute zero helps us understand the fundamental nature of energy matter and time itself. At extremely low temperatures, matter behaves in ways that seem impossible at room temperature. Helium becomes a superfluid that can flow without friction and climb up the walls of containers. Certain metals become superconductors, conducting electricity with zero resistance. These aren't just laboratory curiosities. They're the basis for MRI machines, quantum computers, and the detectors we use to observe the universe. There's also something deeply philosophical about absolute zero. It represents a limit, a boundary that nature has drawn and will not let us cross. We live in a universe of limits: the speed of light, the uncertainty principle, the ultimate cold. These aren't failures of human ingenuity. They're features of reality itself. And learning to understand and accept these limits is part of understanding our place in the cosmos. Imagine just for a moment what it would mean if you could somehow touch absolute zero. Not the near zero temperatures of laboratories, but true absolute zero. If such a thing were possible, the molecules in your fingertip would transfer every quantum of their thermal energy into that infinite cold. The water in your cells would crystallize instantly. Chemical reactions would halt. Your nerves, which depend on electrochemical signals that require molecular motion, would cease to function. In a very real sense, at absolute zero, life itself becomes impossible. Motion, change, time. They all require some degree of warmth, some thermal energy driving the processes we associate with existence. And that brings us to a beautiful realization. We are creatures of warmth in a cold universe. Our body temperature hovers around 310 Kelvin, more than 100 times warmer than the cosmic background. We are impossibly hot compared to the universe around us. Little furnaces of biochemical activity generating heat through the controlled burning of food. Every thought you have, every breath you take, every beat of your heart, all of it depends on maintaining that warmth against the cold of space. The story of absolute zero is ultimately a story about what it means to exist. Existence requires motion, change, energy flow. Perfect stillness, perfect cold, isn't just uncomfortable or deadly. It's the absence of the conditions necessary for anything to happen at all. Temperature isn't just a number on a thermometer. It's a measure of the universe's capacity for change, for process, for becoming. As you settle into sleep tonight, feel the warmth of your blankets, the gentle heat radiating from your body. You're experiencing something profound, the difference between being and nothingness, between activity and absolute stillness. That warmth is the universe's way of allowing you to exist, to think, to dream. But our exploration of cosmic cold has only just begun. We've learned about the theoretical limit of coldness, but now it's time to visit actual cold places. Not laboratories, but natural cosmic freezers where temperatures approach absolute zero without human intervention. In our next chapter, we'll travel to the Boomerang Nebula, the coldest known place in the natural universe where a dying star has created conditions colder than the space around it. We'll discover how death and cold are intimately connected in the cosmos, and why the end of a star's life creates the deepest freeze in nature. The journey from warmth to cold continues. 5,000 light years from Earth in the constellation Centaurus, there exists a place so cold that it defies everything we think we know about the universe. It's colder than the space around it, colder than the cosmic background radiation, colder than anywhere else we've ever found in nature. at minus 272 degrees Celsius, just 1 degree above absolute zero. The Boomerang Nebula holds the record as the coldest known natural place in the entire universe. But here's the mystery that kept astronomers awake at night. How can something in space be colder than space itself? The answer to that question reveals one of the most counterintuitive processes in physics, and it begins with death. The death of a star. The Boomerang Nebula wasn't always a cosmic freezer. 1 million years ago, it was an ordinary star, not unlike our sun, burning hydrogen in its core and radiating warmth into the cosmos. But stars don't live forever. When this particular star exhausted its nuclear fuel, it began the long goodbye that all sun-like stars must face. And in that dying process, it created something extraordinary, a region of space colder than the universe itself has ever been. Naturally. Let me take you back to 1995, when astronomers first realized just how unusual this nebula was. A Swedish astronomer named Raghavendra Sahai was using the 15-meter Swedish ESO sub-millimeter telescope in Chile to study what appeared to be an ordinary planetary nebula. But when he analyzed the spectroscopic data, something didn't make sense. The readings suggested a temperature far lower than anything previously observed in space. Initially, he thought there must be an error, equipment malfunction perhaps, or a mistake in the calculations. But repeated observations confirmed the impossible this nebula was registering at approximately 1 Kelvin, just 1 degree above absolute zero. The discovery sent shockwaves through the astronomical community. How could this be? The entire universe is bathed in cosmic microwave background radiation at 2.7 Kelvin. That's the baseline temperature of space itself, the afterglow of the Big Bang. Nothing should be colder than that baseline, just as nothing in a heated room should be colder than the room's ambient temperature. Yet here was the Boomerang Nebula, somehow more than 1.5 degrees colder than the space surrounding it. It was as if someone had found an ice cube colder than the freezer it was stored in. The answer lies in one of the most elegant principles in physics, the gas expansion cooling effect. You've actually experienced this principle yourself, though you might not have realized it. Have you ever used a can of compressed air to clean your keyboard? Notice how the can gets cold as you spray it. That's gas expansion, cooling in action. As the compressed gas rapidly expands from high pressure to low pressure, it does work on its surroundings, and in doing so, it loses thermal energy. The temperature drops dramatically. Now, imagine that same process but on a cosmic scale and stretched out over thousands of years. That's what's happening in the Boomerang Nebula. The dying star at its center is ejecting its outer layers at an extraordinary rate, about 1/10,000th of a solar mass per year. That might not sound like much, but it's actually 100 times faster than typical planetary nebulae shed their material. And here's the crucial part, that material is being expelled at speeds exceeding 500,000 kilometers per hour, or about 164 kilometers per second. Think about what that means. Gas that was once compressed in the outer layers of a star is suddenly thrust into the near vacuum of space at 500,000 kilometers per hour. It expands violently, doing enormous amounts of work against the pressure gradient. And as it expands, it cools, not gradually, but catastrophically. The temperature plummets from thousands of degrees down to just 1 Kelvin in the span of astronomical moments. But there's more to the story. And this is where it gets really fascinating. The Boomerang Nebula isn't just cold, it's structured in a way that maximizes that cold. When astronomers first observed it with ground-based telescopes, they thought it looked somewhat like a boomerang, hence the name. But in 1998, the Hubble Space Telescope turned its powerful eye toward the nebula and revealed something far more intriguing. The nebula isn't shaped like a boomerang at all. It's structured more like an hourglass or a butterfly, with two massive lobes extending in opposite directions from the dying star at its center. This structure isn't random. It's the result of a complex interplay between the dying star and possibly a companion star orbiting it. Many astronomers now believe that the Boomerang Nebula's central star is actually a binary system, two stars locked in gravitational embrace. As the primary star began to die and swell into a red giant, the companion star's gravity shaped the outflow of material, channeling it into two focused jets shooting out from the poles. This focusing is critical because it concentrates the expansion into narrower streams, which intensifies the cooling effect. Imagine two fire hoses shooting water in opposite directions, but instead of water, it's stellar material. And instead of getting wet, the material is freezing itself through its own rapid expansion. The tighter and faster the flow, the more extreme the cooling. The Boomerang Nebula has achieved the perfect conditions for maximum cooling, rapid mass loss, extremely high ejection velocities, and a geometric structure that focuses that expansion into narrow jets. Now, let's compare this to other planetary nebulae because understanding what makes the Boomerang special tells us something important about how extreme cold can arise in the cosmos. Most planetary nebulae are relatively warm by cosmic standards. The famous Ring Nebula in Lyra, for instance, has a temperature of around 10,000 Kelvin in its ionized regions. The Helix Nebula, one of the closest planetary nebulae to Earth, sits at several thousand Kelvin. These nebulae are hot because they're being actively ionized by ultraviolet radiation from their central stars, which have already transitioned to extremely hot white dwarf stages. The Boomerang Nebula is different because we're catching it at a unique moment in its evolution. The central star hasn't yet become hot enough to significantly ionize the surrounding gas. We're witnessing it in what astronomers call the pre-planetary nebula phase, the brief transition between red giant and white dwarf. During this phase, the star is still cool by stellar standards, around 5,000 Kelvin, so it's not pumping much ultraviolet radiation into its surroundings. Without that heating radiation, the gas expansion cooling effect dominates completely. This raises a fascinating question. Will the Boomerang Nebula stay cold forever? The answer is no. In cosmic terms, its record-breaking cold is temporary. As the central star continues to evolve, it will eventually heat up, becoming a white dwarf with a surface temperature of 100,000 Kelvin or more. When that happens, it will flood the nebula with intense ultraviolet radiation, ionizing the gas and heating it back up to thousands of degrees. The coldest place in the universe will become just another hot planetary nebula, indistinguishable from thousands of others. We're observing it during a fleeting window, perhaps just a few thousand years, when the conditions are perfect for extreme cold. But detecting and measuring this cold presented enormous challenges for astronomers. You can't just point a regular optical telescope at the Boomerang Nebula and take its temperature. The nebula is emitting very little visible light, precisely because it's so cold. Hot objects glow brightly across many wavelengths. Cold objects barely radiate at all. To study the Boomerang Nebula, astronomers had to use submillimeter and radio telescopes instruments designed to detect the faint whispers of radiation from cold molecular gas. The technique they used is called molecular spectroscopy. Different molecules in space emit radiation at very specific wavelengths when they rotate or vibrate. By measuring these emissions, astronomers can determine both what molecules are present and how fast they're moving, which directly correlates to temperature. In the Boomerang Nebula, they focused on carbon monoxide molecules, which are abundant in the ejected stellar material. The narrowness of the spectral lines indicating very slow molecular motion revealed the astonishingly low temperature. This was painstaking work. Raghavendra Sahai spent years observing the nebula, collecting data point by data point, building up a picture of its temperature structure. He discovered that the cold isn't uniform throughout the nebula. The coldest regions are in the densest parts of the expanding lobes, where the gas expansion is most rapid and concentrated. As you move away from these regions toward the edges of the nebula, the temperature gradually rises toward the cosmic background level of 2.7 Kelvin. The Boomerang Nebula is essentially a cold core surrounded by slightly less cold material, all of it suspended in the relatively warmer space around it. There's a beautiful irony here that I want you to appreciate. The Boomerang Nebula is cold because of heat, or rather because of the absence of ongoing heat production. The star at its center was once a furnace fusing hydrogen into helium, generating enough heat and pressure to support itself against gravitational collapse. But when that fusion stopped when the fuel ran out, the star began its collapse and ejection phase. The cold we see now is the direct result of that stellar death, the final exhalation of a star that once blazed with thermonuclear fire. Death and cold are intimately connected in the cosmos, and not just for stars. This is a pattern we see throughout the universe. Active living processes, whether it's nuclear fusion in stars, volcanic activity on planets, or metabolism in living organisms, all generate heat. When those processes cease, cold follows. The Boomerang Nebula is a cosmic tombstone, marking the grave of a star with the coldest temperatures nature can achieve. But here's something that surprised researchers. The Boomerang Nebula isn't just releasing gas, it's also destroying molecules. In the coldest regions of the nebula, molecules are beginning to stick together, forming larger dust grains. This is the beginning of a process that will eventually lead to the formation of new stars and planets from the recycled material of dead stars. The cold of the Boomerang Nebula is facilitating molecular bonding that wouldn't happen at higher temperatures. In a sense, death and cold are giving rise to the building blocks of future creation. The universe wastes nothing. Even the coldest, most desolate places are nurseries for new structures. Let me put the Boomerang Nebula's temperature in perspective for you. At 1 Kelvin, atoms move so slowly that they're barely vibrating. If you could somehow exist at that temperature, time itself would seem to slow down from your perspective. Chemical reactions would be essentially impossible. Even quantum effects become pronounced at such low temperatures. Matter begins to behave in ways that seem alien to our everyday experience. Gases can become superfluids flowing without friction. Quantum tunneling becomes observable. The distinction between individual particles starts to blur. At temperatures this low, we're not just talking about cold. We're talking about a different regime of physics altogether. And yet, despite being the coldest natural place known, the Boomerang Nebula still isn't at absolute zero. That last degree matters. That final Kelvin represents the quantum zero-point energy we discussed earlier, the irreducible jitter that prevents anything from being completely, utterly still. Even in nature's deepest freeze, the universe maintains its quantum heartbeat. The discovery of the Boomerang Nebula taught astronomers that they had underestimated nature's capacity for extreme conditions. Before its discovery, many assumed that the cosmic microwave background set a firm lower limit on natural temperatures. Why would anything be colder than its surroundings? But the boomerang showed that local processes, in this case rapid gas expansion, can temporarily overcome ambient conditions. It's a reminder that the universe is full of surprises, that our assumptions about what's possible are often too conservative. Could there be places even colder than the Boomerang Nebula waiting to be discovered? Possibly. Perhaps somewhere in the universe another dying star is ejecting material even faster, creating an even more extreme freeze. Or perhaps some exotic astrophysical process we haven't imagined yet is capable of producing temperatures even closer to absolute zero. The universe is vast, and we've only examined a tiny fraction of it. The Boomerang Nebula holds the record for now, but records, as we know, are made to be broken. As you rest tonight, consider this. The coldest place in the natural universe was created by the death of a star. All that warmth, all that nuclear fire that burned for billions of years, ultimately gave way to the deepest cold nature has ever produced. There's a lesson in that about endings and transformations, about how even in death, the universe finds ways to surprise us, to create conditions that push the boundaries of what seems possible. The Boomerang Nebula is slowly dissipating now, its cold material mixing with the warmer interstellar medium. In a few tens of thousands of years, it will warm up as its central star heats and ionizes it. But for this brief cosmic moment, it stands as a monument to the power of expansion, the intimacy of death and cold, and nature's ability to reach temperatures that rival our most advanced laboratories. We've now seen where absolute cold exists naturally in the cosmos. But this raises new questions. How do we actually measure such extreme cold from Earth? How do we know that space itself has a temperature? And what does it mean for something to have a temperature when there's essentially nothing there? These questions lead us into the remarkable story of how we discovered the temperature of space itself and what that discovery revealed about the birth of our universe. In 1964, two scientists at Bell Telephone Laboratories in New Jersey were trying to eliminate a persistent, annoying hiss from their radio antenna. No matter what they did, scrubbing the equipment, removing pigeon droppings, reorienting the dish, the noise remained. They had no idea they were listening to the birth cry of the universe itself, a whisper of ancient light that would prove space has a temperature, and that temperature tells the story of creation. This accidental discovery would win Arno Penzias and Robert Wilson. The Nobel Prize fundamentally changed our understanding of cosmology and answer a question that had puzzled scientists for decades. If space is a vacuum essentially empty, how can it have a temperature at all? The story of how we discovered the temperature of space begins not in 1964, but nearly 2 decades earlier, with a prediction that most physicists ignored. In 1948, a team of scientists, including Ralph Alpher and Robert Herman, were working on the mathematics of the Big Bang Theory, which was still controversial at the time. They realized that if the universe really had begun in a hot, dense state and then expanded, there should be leftover radiation from that primordial fireball still permeating space today. They even calculated what temperature that radiation should have cooled to, after billions of years of cosmic expansion, about 5 degrees above absolute zero. Their prediction was published in respected journals, but it went largely unnoticed. The technology to detect such faint radiation didn't exist yet, and many physicists still favored the competing steady-state theory, which proposed that the universe had no beginning and thus no primordial radiation. Alpher and Hermann's prediction sat in the literature like a treasure map that no one knew how to read, until Penzias and Wilson stumbled upon the treasure by accident. Let me set the scene for you. It's May 1964, and Penzias and Wilson are working with a large horn antenna originally built for satellite communications. They're trying to use it for radio astronomy, but there's a problem. No matter where they point the antenna, no matter what time of day or night, they detect excess noise. It's uniform, persistent, and utterly baffling. At first, they suspect equipment problems. They check every connection, every component. Nothing. Then they notice that pigeons have been nesting in the antenna, leaving what Penzias would later delicately describe as a white dielectric material coating the inside. Surely this must be causing interference. They clean everything meticulously, even going so far as to trap the pigeons and relocate them. The birds kept coming back, so eventually Penzias and Wilson had to make the difficult decision to have them removed permanently. But even after all this, the hiss remained. Same intensity, same character day and night, summer and winter. No matter which direction they pointed the antenna, it corresponded to a temperature of about 3.5 Kelvin, slightly higher than the modern refined measurement. Penzias and Wilson were stumped. What they were detecting seemed to be coming from everywhere at once, uniformly distributed across the entire sky. That shouldn't be possible from any conventional source. Meanwhile, just 30 miles away at Princeton University, a physicist named Robert Dicke was preparing to search for exactly what Penzias and Wilson had already found. Dicke had independently reached the same conclusion as Alpher and Herman. The Big Bang should have left behind a background radiation with a temperature of a few degrees Kelvin. He was building equipment to detect it when a mutual colleague mentioned the strange uniform noise that Penzias and Wilson couldn't explain. Dicke immediately understood what it was. When his team heard the news, Dickey reportedly said, "Well, boys, we've been scooped." The pieces fell into place rapidly after that. Penzias and Wilson hadn't just been hearing equipment noise. They had been detecting the cosmic microwave background radiation, the CMB, the cooled remnant of the Big Bang itself. This discovery was so important that it effectively ended the debate between Big Bang and steady-state cosmology. Here was direct observational evidence that the universe had indeed begun in a hot, dense state and had been cooling ever since. But what exactly is the cosmic microwave background, and why does it give space a temperature? This is where many people get confused. So, let's clarify. When we say space has a temperature of 2.7 Kelvin, we're not saying the vacuum itself is hot or cold. Vacuum by definition is empty. It has no temperature because there's nothing there to have kinetic energy. What we're really measuring is the temperature of the photons, the particles of light that fill space. Think of it this way: space isn't truly empty. It's permeated by electromagnetic radiation, primarily in the microwave range left over from the early universe. These photons have been traveling through space for over 13 billion years, and as the universe has expanded, their wavelengths have stretched, cooling them from the intense heat of the early universe down to just 2.7 degrees above absolute zero. When we measure the temperature of space, we're measuring the temperature that a perfect blackbody absorber would reach if placed in space and allowed to come into thermal equilibrium with this radiation bath. Let me take you back even further to understand where these photons came from and why they tell us so much about the universe's history. In the first moments after the Big Bang, the universe was unimaginably hot and dense, filled with a plasma of subatomic particles and photons. Temperature estimates for the first fraction of a second range into the trillions of degrees. At those temperatures, matter as we know it couldn't exist. Protons, neutrons, and electrons existed, but they couldn't combine into atoms because the photons were so energetic they would immediately knock any atoms apart. As the universe expanded, it cooled. This is a fundamental principle. Expansion leads to cooling. It's the same principle we saw in the Boomerang Nebula, but on a cosmic scale. About 380,000 years after the Big Bang, the universe had cooled enough to about 3,000 Kelvin for electrons and protons to combine into neutral hydrogen atoms. This moment is called recombination, and it's one of the most important events in cosmic history. Before recombination, the universe was opaque. Photons couldn't travel far before scattering off free electrons. It was like trying to see through fog. But when atoms formed, suddenly photons could travel freely. The universe became transparent. The light that was released at that moment has been traveling through space ever since, and that's what Penzias and Wilson detected. The CMB is literally a snapshot of what the universe looked like 380,000 years after the Big Bang, the oldest light we can possibly observe. But here's the remarkable part: that light which was emitted at about 3,000 Kelvin has now cooled to 2.7 Kelvin. The universe has expanded by a factor of about 1,100 since recombination, and the wavelengths of the photons have stretched by exactly that same factor. This is called cosmological redshift. It's direct evidence of the universe's expansion encoded in the temperature of space itself. Now, you might be wondering, how do we actually measure the temperature of this radiation after all, too? 7 Kelvin is incredibly cold, and the radiation is extremely faint. The answer involves some of the most sophisticated instruments humans have ever built, satellites designed specifically to map the cosmic microwave background with exquisite precision. The first major advance after Penzias and Wilson came in 1989 with the launch of the Cosmic Background Explorer, COBE. This satellite carried instruments designed to measure the spectrum and temperature of the CMB across the entire sky. The results were stunning. The CMB has an almost perfect blackbody spectrum, meaning it matches the theoretical prediction for radiation from a uniform temperature source almost exactly. The temperature COBE measured was 2.725 Kelvin plus or minus a tiny fraction. This precision confirmed beyond doubt that we were seeing primordial radiation from the Big Bang. But Kobe revealed something even more exciting: tiny variations in temperature across the sky, fluctuations of about 1 part in 100,000. These variations are crucial because they represent the seeds of all cosmic structure. Regions that were slightly denser and cooler in the early universe eventually collapsed under gravity to form galaxies, stars, and planets. The tiny temperature fluctuations in the CMB are in a very real sense the blueprint for everything we see in the universe today, including Earth and everyone on it. The next leap came with the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001. WMAP measured the CMB with much higher resolution, creating detailed maps of the temperature variations across the sky. These maps allowed cosmologists to determine fundamental properties of the universe with unprecedented precision: its age 13.8 billion years, its geometry flat, its composition about 5% ordinary matter, 27% dark matter, and 68% dark energy. All of this from measuring temperature fluctuations of a few millionths of a degree in the cosmic microwave background. It's remarkable when you think about it. The temperature of space isn't just a random number. It's a fossil, a relic that preserves information about the universe's birth and evolution, waiting to be decoded by anyone with the right instruments and knowledge. Then came Planck, a European Space Agency satellite launched in 2009. Planck measured the CMB with even greater precision, refining our measurements of the universe's properties and revealing subtle features that tested our cosmological models. The current best measurement of the CMB temperature is 2.7255 Kelvin, accurate to within a few thousandths of a degree. Think about that precision. We can measure the average temperature of the entire universe to 4 decimal places. But here's something that surprises many people. The CMB temperature isn't perfectly uniform across the sky. There's a dipole pattern, a slight difference between one direction and another caused by Earth's motion through space. As we move towards certain parts of the sky, the CMB photons we encounter are slightly blue-shifted, higher in energy, appearing slightly warmer. In the opposite direction, they're red-shifted, appearing slightly cooler. This dipole tells us that our solar system is moving at about 370 kilometers per second relative to the CMB rest frame, carried along by the motion of the Milky Way galaxy itself. This raises a fascinating philosophical point. The cosmic microwave background defines a kind of universal rest frame, a cosmic reference point. In special relativity, we learned that there's no absolute rest frame, that all motion is relative. And that's still true for local measurements. But on cosmic scales, the CMB provides a natural reference frame. If you're at rest with respect to the CMB, you see it as uniform in all directions. If you're moving, you see a dipole pattern. In this sense, the temperature of space gives us a way to measure our motion through the universe itself. Now, let's address a common misconception. Many people hear that space has a temperature of 2.7 Kelvin and assume that means anything placed in space will quickly cool to that temperature. But that's not quite right, and understanding why reveals something crucial about how heat transfer works in vacuum. Temperature, remember, is a measure of molecular kinetic energy. Heat can be transferred through 3 mechanisms: conduction, which requires physical contact; convection, which requires a fluid medium like air or water; and radiation, the emission of electromagnetic waves. In space, there's no air, no medium for conduction or convection. The only way to lose heat is through radiation, and radiation is actually quite slow for objects that aren't extremely hot. Consider a human body at 310 Kelvin. We radiate heat as infrared radiation, but we also absorb radiation from our surroundings, including the CMB. In space, wearing a proper spacesuit, you'd actually have more trouble staying cool than staying warm. The vacuum is an excellent insulator. This is why spacecraft need active cooling systems. They can't rely on convection to carry heat away. They must radiate it, which is much less efficient. There's a beautiful application of this principle in your everyday life. A thermos bottle or vacuum flask works by creating a vacuum between two walls. Without air for conduction and convection, heat transfer is minimized. The same principle that keeps your coffee hot is what makes thermal management in space so challenging. The vacuum of space, despite being at 2.7 Kelvin, is actually an insulator, not a coolant. This brings us to astronauts and spacecraft. You might wonder, if space is so cold, why don't astronauts freeze? The answer is, they're actually more likely to overheat. The International Space Station, for example, generates a lot of heat from electronics, human bodies, and solar radiation. That heat has to be radiated away through large radiator panels. Without these, the station would cook its occupants. The spacesuits astronauts wear during spacewalks have sophisticated cooling systems to remove body heat and heat from the sun, not primarily to keep them warm. But here's where it gets interesting. If an astronaut's cooling system failed, they wouldn't freeze immediately. They'd overheat first from their own metabolic heat and absorb solar radiation. Eventually, after death, their body would radiate away its heat and slowly cool toward the temperature of the CMB. But this would take hours, not seconds. Space is cold, but it's not a quick cold. It's a patient insulating cold that lets heat escape only slowly through radiation. The discovery of the CMB temperature also solved another mystery. Why is the night sky dark? This question, known as Olber's paradox, troubled astronomers for centuries. If the universe is infinite and filled with stars, shouldn't every direction we look eventually hit a star's surface? Shouldn't the night sky be as bright as the surface of the sun? The answer lies in the finite age of the universe and its expansion. Light from distant stars hasn't had time to reach us yet, and the light that has reached us has been red-shifted by expansion, cooling it from visible light to microwaves. The darkness of the night sky is, in a sense, the coolness of the cosmic microwave background, made visible, or rather, made invisible. Here's something that might make you pause. Every cubic centimeter of space, even the emptiest regions between galaxies, contains about 400 CMB photons. Space is not as empty as we imagine. It's filled with these ancient photons, the cooled radiation from the Big Bang, creating a uniform bath at 2.7 Kelvin. You're surrounded by them right now. They pass through your body constantly, billions upon billions of them. Every second, ghosts of the universe's birth, flowing through you as you rest. And these photons carry information. By studying their exact temperature, their distribution across the sky, and their polarization, cosmologists can test theories about the universe's earliest moments, potentially even finding evidence of cosmic inflation, the exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. The temperature of space is not just a number. It's a library of cosmic history waiting to be read. As you drift towards sleep, consider the profound strangeness of what we've discovered. The vacuum of space, which seems like pure emptiness, actually has a temperature. Not because the vacuum itself is hot or cold, but because it's permeated by ancient light, stretched and cooled by billions of years of the cosmic expansion. That temperature, 2.7 Kelvin, connects us directly to the universe's origin. It's a whisper from the Big Bang, still audible 13.8 billion years later, if you have the ears to hear it. We've learned how we measure the cosmic cold and what that measurement tells us about the universe's history. But now we face a paradox that confused early space explorers and still trips up many people today. If space is so cold, why don't things freeze instantly? Why is vacuum actually one of the best insulators known? The answer to these questions reveals surprising truths about heat, cold, and the nature of nothingness itself. On March 18, 1965, Soviet cosmonaut Alexei Leonov became the first human to walk in space. But what should have been a triumphant 12 minutes nearly became a disaster. His spacesuit exposed to the vacuum and extreme temperatures of space began to malfunction. Not from freezing as you might expect, but from overheating. Leonov was cooking inside his suit, sweating profusely, his visor fogging up. By the time he struggled back into the airlock, he'd lost 6 kilograms of body weight through perspiration. This near catastrophe revealed a counterintuitive truth. In the frozen vacuum of space, staying cool is often harder than staying warm. How can this be? If space is at 2.7 Kelvin, nearly absolute zero, why wasn't Leonov freezing? The answer lies in one of physics' most beautiful paradoxes, one that challenges our everyday intuitions about heat, cold, and the very meaning of temperature in a place where there's essentially nothing at all. To understand this paradox, we need to explore the 3 fundamental ways heat moves through the universe: conduction, convection, and radiation. These aren't just abstract concepts. They're happening around you right now as you listen. The warmth you feel from your blankets, that's primarily conduction. If you're in a room with air circulation, that's convection at work. And the gentle warmth of sunlight streaming through a window, that's radiation. In our everyday world, all 3 work together, creating an intuitive sense of how heat and cold behave. But space strips away 2 of these mechanisms entirely, leaving only radiation, and that changes everything. Let's start with conduction, because it's probably the most familiar. Conduction is heat transfer through direct physical contact. When you touch a cold metal railing on a winter morning, heat flows from your warm hand into the cold metal through molecular collisions. The faster-moving molecules in your skin collide with slower-moving molecules in the metal, transferring kinetic energy. This is why metal feels colder than wood at the same temperature. Metal conducts heat away from your hand much more efficiently. But here's the crucial point. Conduction requires matter. It requires molecules or atoms in contact with each other, creating a pathway for energy transfer. In space, there is no such pathway. Space is a vacuum, meaning there are vanishingly few particles to conduct heat. The few atoms that do exist, perhaps 1 per cubic centimeter in interstellar space, are so sparsely distributed that they're essentially irrelevant for heat transfer. When you're floating in space, there's nothing to conduct your body heat away. It's as if you're surrounded by the most perfect insulation imaginable. Now, let's consider convection, which is equally impossible in space. Convection occurs when a fluid like air or water carries heat from one place to another through bulk motion. When you boil water, hot water rises to the surface while cooler water sinks to the bottom, creating a circulation pattern. When you feel a breeze on a hot day, that's convection cooling your skin as moving air carries heat away from your body. We rely on convection constantly without thinking about it. Your body sheds about 100 watts of heat, continuously, about the same as a bright incandescent light bulb. In normal air, much of this heat is carried away by convection. Warm air rises from your skin, replaced by cooler air, creating a constant circulation that keeps you from overheating. But in space, there's no air to circulate. There's no fluid medium to carry heat away. Convection simply doesn't exist. Your body's heat has nowhere to go through convective transfer. This leaves only radiation, the 3rd mechanism of heat transfer, and the only one that works in vacuum. Radiation is the emission of electromagnetic waves. Every object with a temperature above absolute zero emits thermal radiation. You're emitting infrared radiation right now. The sun heats Earth through radiation, traveling across 93 million miles of vacuum. Radiation doesn't need a medium. It travels through empty space at the speed of light. But here's the problem with radiation. As a cooling mechanism, it's slow. The amount of heat an object radiates depends on its temperature raised to the 4th power, according to the Stefan-Boltzmann law. Very hot objects radiate powerfully. The sun's surface at 5,800 Kelvin radiates enormous amounts of energy. But objects at human body temperature around 310 Kelvin radiate much less. In space, an astronaut can only lose heat through radiation. And at body temperature, that process is relatively slow. too slow to keep up with the heat your body generates through metabolism. Let me quantify this for you. A human body at rest produces about 100 watts of heat. In normal air on Earth, convection and conduction easily carry this away. But in space, radiating 100 watts requires a significant surface area. A human body doesn't have enough surface area to radiate away all its metabolic heat efficiently. Without active cooling systems, an astronaut would slowly overheat even in the frigid vacuum of space. This is the paradox. Surrounded by near absolute zero cold, you'd cook in your own heat. This reality fundamentally shaped the design of spacesuits. Early space program engineers initially worried about keeping astronauts warm. They quickly realized the opposite problem was more pressing. Modern spacesuits include sophisticated water cooling systems. A network of thin tubes carrying chilled water runs through an undergarment worn against the astronaut's skin. This water absorbs body heat through conduction and carries it to radiator panels on the outside of the spacecraft, or suit, where it can finally be radiated into space. Without this system, spacewalks would be impossible. The Apollo 13 mission provides a dramatic real-world example of space temperature paradoxes in action. On April 13, 1970, an oxygen tank exploded aboard the spacecraft, crippling the command module. The crew had to shut down most systems to conserve power and retreat to the lunar module, which was designed to support 2 people for 2 days, but now had to keep 3 people alive for 4 days. One of their most serious problems wasn't freezing, though the cabin temperature did drop to about 3 degrees Celsius. It was managing heat distribution. The spacecraft's electronics still generated heat, but with reduced power to the environmental controls, that heat couldn't be properly distributed through convection inside the cabin or radiated away efficiently into space. Certain components risked overheating while the crew members shivered. Jim Lovell later described condensation forming on the walls as moisture from their breath, unable to be properly vented, began to freeze on the coldest surfaces. Meanwhile, some electronic equipment was dangerously hot. They were experiencing both extremes simultaneously, a temperature management nightmare in a disabled spacecraft. Think about the lesson here. In space, temperature isn't just about how hot or cold the environment is. It's about how efficiently you can shed or retain heat. The vacuum of space creates a bizarre situation where you're thermally isolated, able to neither gain nor lose heat quickly through conventional means. You're trapped in your own thermal envelope, and managing that envelope becomes a matter of life and death. Now, let's explore why this matters for spacecraft design. The International Space Station orbits Earth at an altitude of about 400 kilometers. On the sunlit side of its orbit, the station is exposed to the full intensity of solar radiation, heating exterior surfaces to over 120 degrees Celsius. In Earth's shadow, those same surfaces can drop to minus 150 degrees Celsius. That's a temperature swing of 270 degrees every 90 minutes as the station orbits. How does the ISS manage this? Certainly not through conduction or convection with the surrounding space. Instead, it uses massive radiator panels over 1,600 square meters of surface area, designed specifically to radiate excess heat into space. These radiators contain ammonia that circulates through the station, collecting heat from electronics experiments, and the crew then carrying it to the radiators, where it's emitted as infrared radiation. The system is so critical that if it fails, the station has only about 2 hours before interior temperatures reach dangerous levels. 2 hours surrounded by the cold of space, and the crew would be in danger from overheating, not freezing. The James Webb Space Telescope, launched in 2021, takes this principle to an extreme. Webb operates at incredibly cold temperatures, with its instruments cooled to about 7 Kelvin, necessary for detecting faint infrared signals from distant galaxies. But one side of the telescope faces the sun, Earth and Moon, all heat sources. To protect the cold instruments, Webb has a tennis court-sized sun shield made of 5 layers of special material. This shield doesn't work by conducting or convecting heat away. It works by reflecting solar radiation and allowing each layer to radiate heat to the next layer, creating a temperature gradient. The sun-facing side can reach 85 degrees Celsius, while the science instruments on the other side stay at 7 Kelvin. A difference of about 78 degrees maintained purely through controlling radiation, with no other heat transfer mechanisms available. Let me share a thought experiment that really drives this point home. Imagine you're suddenly transported into space without a spacesuit. What happens? Movies and TV shows often depict people instantly freezing solid ice crystals forming on their skin. But that's not what would happen. Your immediate problems would be lack of oxygen and the formation of water vapor bubbles in your bloodstream due to the pressure drop. You'd lose consciousness in about 15 seconds from lack of oxygen. You'd die within a minute or two. But you wouldn't freeze not quickly anyway. Your body would retain its heat for minutes or even hours because there's no efficient mechanism to remove it. The vacuum is an insulator, not a coolant. Eventually, your body would radiate its heat away and cool toward the temperature of the CMB, but this would be a slow process taking many hours. You'd be long dead from other causes before you froze. This counterintuitive reality has practical implications beyond space travel. Vacuum insulation is used in many everyday technologies precisely because vacuum is such a poor conductor of heat. Vacuum-insulated Windows thermoses and even some high-performance building materials exploit the same principle that makes space such a paradoxical thermal environment. By removing the medium for conduction and convection, you create excellent insulation regardless of the temperature difference across the vacuum gap. There's also a subtle point about the meaning of cold that this discussion reveals. When we say something is cold, we usually mean it will absorb heat from warmer objects that touch it. Ice is cold because it conducts heat away from your fingers. But space can't absorb your heat through conduction because there's nothing to conduct heat into. In this sense, space isn't really cold in the way we normally use that word. It's more accurate to say space has a low radiation temperature. It will slowly absorb heat through radiation, but that's a fundamentally different process than the conductive cold of an ice cube or the convective cold of winter wind. Consider the difference between Earth's coldest places and the vacuum of space. On the summit of Antarctica's dome, Argus temperatures can drop below minus 90 degrees Celsius. That's brutally cold enough to kill you in minutes if you're unprotected. But it's a very different kind of cold than space. In Antarctica, you're surrounded by air at minus 90 degrees. That air conducts heat away from your body. Wind, if present, carries heat away through convection. You lose heat rapidly through multiple mechanisms. In space, at 2.7 Kelvin, you lose heat only through radiation, which is far less efficient at body temperature. Paradoxically, you could survive longer in the vacuum of space at 7 Kelvin with a supply of oxygen, of course, than in Antarctic air at minus 90 Celsius without proper protection, simply because the vacuum can't efficiently steal your body heat. This brings us to one of the most elegant demonstrations of these principles, the Dewar flask, or thermos bottle, invented by James Dewar in 1892. Dewar was trying to store liquefied gases at extremely low temperatures, and he realized that the best insulation was nothing at all. His flask consists of two walls with a vacuum between them. The vacuum prevents heat loss through conduction and convection. The walls are coated with reflective material to minimize radiative heat transfer. This simple design, exploiting the insulating properties of vacuum, can keep liquids hot or cold for hours, maintaining temperature differences of over 100 degrees Celsius, with the environment using nothing but empty space as insulation. You're using Dewar's invention every time you use a thermos. That same principle keeps astronauts from freezing and satellites from losing their carefully regulated internal temperatures. It's a perfect example of how understanding the fundamental physics of heat transfer in different environments leads to practical innovations. Now, here's a question. Worth pondering, does temperature even have meaning in a perfect vacuum? If there are no particles, nothing to have. Kinetic energy, can we speak of temperature at all? This gets into deep philosophical territory about the nature of physical properties. Most physicists would say that a true perfect vacuum has no temperature, or rather, the concept doesn't apply. But space isn't a perfect vacuum. It contains the CMB photons we discussed earlier, sparse atoms and molecules, cosmic rays, magnetic fields. These do have temperature in a meaningful sense. But the temperature of these components isn't directly experienced by an object in space because there's not enough matter present for efficient thermal contact. The object only experiences radiative heating and cooling, creating this strange thermal isolation we have been exploring. This isolation has strange consequences. Two objects floating side by side in space, both exposed to the same radiation field, can be at completely different temperatures if they have different surface properties. A shiny reflective object might stay relatively cool by reflecting solar radiation, while a black absorbing object next to it could be much hotter from absorbing that same radiation. Neither is in thermal equilibrium with space, in the way we think about objects reaching equilibrium with their environment on Earth. They're each in their own separate radiative balance, thermally isolated from each other, despite being physically close. The International Space Station demonstrates this vividly. Astronauts doing spacewalks can be simultaneously too hot on one side of their body facing the sun and too cold on the other side facing away. The suit's cooling system has to manage this asymmetry, cooling the sun-facing side while maintaining warmth on the shadowed side. It's like being in front of a roaring fireplace while your back is pressed against ice, except the fireplace is unfiltered solar radiation, and the ice is the radiative cold of space. As you rest tonight, think about the strange nature of cold in a vacuum. We've built intuitions about temperature based on our experience with air, water, and solid objects, all environments where conduction and convection dominate. But the universe is mostly vacuum, where those intuitions fail. The cold of space isn't the aggressive heat-stealing cold of ice or winter air. It's a passive insulating cold that doesn't actively take your warmth, but simply offers no easy way for you to shed it. In the coldest environment in the universe, you'd be in danger of overheating. There's something beautifully paradoxical about that, don't you think? Understanding this paradox reveals something profound about the nature of temperature itself. Temperature isn't an inherent property of space. It's a property of matter and radiation within space. And heat flow isn't about hot and cold automatically equalizing. It's about mechanisms, pathways for energy transfer. When those pathways don't exist, temperature differences can persist. Indefinitely, objects maintaining their own thermal states in isolation from their surroundings. Space, despite being colder than we can easily imagine, respects those isolations, allowing each object to chart its own thermal destiny through the delicate balance of absorbed and radiated energy. This thermal journey through space brings us to perhaps the most profound question of all. How did the universe go from unimaginably hot to nearly absolute zero? And where is that journey taking us? The story of the universe's temperature is the story of time itself. 13.8 billion years ago, the universe was hotter than anything you can imagine. Not just hotter than the sun's core, not just hotter than a supernova. At the very first moment, the Planck epoch temperatures reached 10 to the power of 32 Kelvin. That's a 1 followed by 32 zeros. At that temperature, the distinction between matter and energy dissolves completely. The fundamental forces of physics unified into a single force. Time and space themselves were quantum foam fluctuating wildly. Today, that same universe sits at 2.7 Kelvin, just barely above absolute zero. How did we get from incomprehensible heat to near perfect cold? That journey is nothing less than the story of time itself. Understanding how the universe cooled reveals not just the past, but also our future. Because the universe is still cooling, still expanding, heading toward an ultimate fate that physicists call the heat death, or the the Big Freeze. Tonight, we're going to trace that thermal journey from the hottest moment that ever existed to the coldest possible future, and discover what temperature can tell us about the nature of time, entropy, and existence itself. Let's begin at the very beginning, though we must admit immediately that we can't truly go all the way back to time zero. There's a wall in our understanding, and it occurs at what's called the Planck time, about 10 to the power of negative 43 seconds after the Big Bang. Before that moment, our physics breaks down. We'd need a complete theory of quantum gravity to describe what happened, and we don't have one yet. But at the Planck time, we can start to speak with some confidence, and what we find there is almost beyond comprehension. At the Planck epoch, the universe was unimaginably dense and hot. The temperature was about 10 to the power of 32 Kelvin. To give you some perspective, the core of the Sun is about 15 million Kelvin. The hottest temperature ever created on Earth in the Large Hadron Collider is about 5.5 trillion Kelvin. The Planck temperature is about 20 million trillion times hotter than that. At these temperatures, particles as we know them couldn't exist. Even quarks and electrons would be broken down into more fundamental components. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single superforce. But this state didn't last. The universe was expanding, and expansion means cooling. This is an iron law of cosmology, one we've already seen operating in the Boomerang Nebula, but now on the grandest possible scale. As space expands, the energy density decreases. Temperature drops. And as temperature drops, the universe undergoes phase transitions, moments when its fundamental character changes, like water freezing into ice. The first major phase transition happened at about 10 to the power of negative 36 seconds, when the universe had cooled to around 10 to the power of 27 Kelvin. This is when gravity separated from the other forces. Shortly after, at around 10 to the power of negative 32 seconds, something extraordinary occurred: cosmic inflation. For a brief moment, shorter than the blink of an eye, the universe expanded exponentially, doubling in size at least 60 times in a fraction of a second. This inflation stretched the universe from smaller than an atom to perhaps the size of a grapefruit, smoothing out irregularities and setting the stage for everything that would follow. Why did inflation happen? The most widely accepted theory is that it was driven by a field called the inflaton field, which was in a high-energy state. When this field dropped to a lower energy state, it released enormous energy, driving the exponential expansion and reheating the universe to extremely high temperatures, though not as hot as the initial Planck epoch. This is one of the most important moments in cosmic history, and it happened because of a change in the energy state of a field, fundamentally a thermal process on an unimaginable scale. After inflation ended, the universe continued expanding, but now at a more sedate pace. As it expanded, it cooled. Between about 10 to the power of negative 12 seconds and 10 to the power of negative 6 seconds after the Big Bang, the universe cooled from about 10 to the power of 15 Kelvin to about 10 trillion Kelvin. During this time, called the quark epoch, the universe was filled with a dense soup of quarks, gluons, and other elementary particles. It was too hot for quarks to bind together into protons and neutrons. The universe was a seething plasma of fundamental particles colliding and annihilating at incredible rates. Then, at about 1 microsecond after the Big Bang, when the temperature had dropped to around 10 trillion Kelvin, another phase transition occurred. The universe had cooled enough for quarks to combine into hadrons, particles like protons and neutrons. This moment, the transition from the quark epoch to the hadron epoch, marked the first time that the building blocks of atomic nuclei could exist. Before this, matter, as we know it, was impossible. After this, we're one step closer to the universe we inhabit today. But the universe was still extraordinarily hot. For the next few seconds, from 1 microsecond to about 10 seconds after the Big Bang, protons and neutrons existed in thermal equilibrium with radiation and lighter particles. The temperature during this time ranged from about 10 trillion Kelvin down to about 1 billion Kelvin. Think about that for a moment. 10 seconds after its birth, the universe was still hotter than the center of the hottest stars we observe today. The universe has been cooling for 13.8 billion years, and it's still hot compared to absolute zero. But compared to its birth, it's already frigid. Between 10 seconds and about 20 minutes after the Big Bang, something crucial happened. Big Bang nucleosynthesis. At these temperatures, roughly 1 billion Kelvin down to about 100 million Kelvin, nuclear fusion could occur just as it does in stellar cores today. Protons and neutrons fuse together, forming the first atomic nuclei: deuterium, helium, 3 helium, 4, and traces of lithium-7. This process created the first chemical elements beyond hydrogen setting, the elemental composition of the universe. About 75% hydrogen and 25% helium by mass, a ratio we still observe in the oldest, most pristine regions of the universe today. This nucleosynthesis era is one of the great triumphs of cosmology. Physicists predicted, based purely on theory, what the abundances of these light elements should be. When astronomers measured them observationally, the match was stunning. The universe really did go through this hot, dense phase where nuclear fusion occurred everywhere at once. The helium in your breath, the deuterium in the ocean, they weren't made in stars. They're fossils from the first 20 minutes of cosmic history, forged when the entire universe was a fusion reactor. After nucleosynthesis ended, the universe continued cooling, but now we enter a long, relatively uneventful period cosmologists call the photon epoch, or the radiation era. For about 380,000 years, the universe was still too hot for atoms to form. Anytime an electron tried to bind to a nucleus, a high-energy photon would knock it loose again. The universe was opaque, a fog of plasma where light couldn't travel far before scattering. The temperature during this era ranged from about 100 million Kelvin down to about 3,000 Kelvin. And then 380,000 years after the Big Bang, something beautiful happened. The universe had cooled to about 3,000 Kelvin, roughly half the temperature of the sun's surface. At this temperature, electrons could finally bind permanently to nuclei, forming the first neutral atoms, mostly hydrogen and helium. This moment is called recombination, and it transformed the universe from opaque to transparent. Photons could suddenly travel freely without constant scattering. The universe lit up, or rather became clear for the first time. The light released at recombination is the cosmic microwave background we discussed earlier. When it was emitted, it had a temperature of 3,000 Kelvin, corresponding to orange-red visible light. But as the universe has expanded over the last 13.8 billion years, those photons have been stretched redshifted cooling from 3,000 Kelvin down to 2.7 Kelvin. The CMB is literally the cooled afterglow of recombination stretched across the entire sky, a fossil record of the moment the universe became transparent. After recombination, the universe entered what cosmologists call the Dark Ages, with atoms formed and light traveling freely, but no stars yet born to illuminate the darkness. The universe was truly dark. It was also cooling rapidly as it expanded. Within a few million years, the temperature of the universe had dropped to a few hundred Kelvin, then to a few tens of Kelvin. The cosmic microwave background, already redshifted into the infrared, continued its inexorable cooling toward the microwave temperatures we observe today. But the universe wasn't entirely quiet during the Dark Ages. In slightly denser regions where matter had clumped together, just a bit more than average gravity was pulling material together. These density fluctuations, which we can detect as tiny temperature variations in the CMB, were the seeds of all cosmic structure. Over millions of years, these regions collapse further, heating up through gravitational compression. Eventually, about 100 to 200 million years after the Big Bang, the first stars ignited, ending the Dark Ages and beginning what's called the Epoch of Ionization. These first stars, called population 3 stars, were very different from stars today. They formed from pristine hydrogen and helium with no heavier elements yet created. They were massive, perhaps hundreds of times the mass of our sun, and incredibly hot. Their intense radiation ionized the hydrogen gas around them, creating bubbles of ionized plasma that grew and merged. Within a few hundred million years, the entire universe was reionized, clearing the cosmic fog once more. Here's something fascinating at the moment. The first stars formed the universe as a whole had cooled to perhaps 20 to 30 Kelvin. But locally inside these stars, temperatures soared to tens of millions of Kelvin, hot enough for nuclear fusion. For the first time since the Big Bang, nucleosynthesis fusion was creating new elements, but now it was localized, happening in stellar cores rather than everywhere at once. The universe had transitioned from a uniformly hot state to a mostly cold state with isolated pockets of extreme heat. This is still true today. Most of the universe is cold near the CMB temperature, but stars, galaxies, and clusters create islands of warmth in an otherwise frigid cosmos. As stars evolved, fused elements, and died in supernova explosions, they enriched the cosmos with heavier elements. Carbon, nitrogen, oxygen, iron, all the elements necessary for planets and life, were manufactured in stellar furnaces and scattered across space. Second and third generations of stars formed from this enriched material. Galaxies grew and evolved. About 9 billion years after the Big Bang, roughly 4.6 billion years ago, our own sun formed from a cloud of gas and dust enriched by previous generations of stars. The thermal history of the universe had brought us to this point, a stable, long-lived star with a family of planets, one of which would develop life. Throughout this entire history, from the Planck epoch to today, the universe has been cooling, but the cooling hasn't been uniform or steady. Phase transitions punctuated the smooth expansion moments when the falling temperature triggered fundamental changes in the universe's state. These transitions are similar to what happens when you cool water. At 100 degrees Celsius, water boils or condenses. At 0 degrees Celsius, it freezes or melts. The universe has undergone its own phase transitions as it cooled. The separation of forces, the formation of hadrons, the creation of atomic nuclei, the formation of atoms, the ignition of the first stars. Each transition fundamentally altered what the universe was and what it could become. Now let's turn to the future, because the universe's thermal journey is far from over. Right now, 13.8 billion years after the Big Bang, the universe is still expanding. In fact, that expansion is accelerating, driven by something we call dark energy. As the universe continues to expand, it will continue to cool. The cosmic microwave background, currently at 2.7 Kelvin, will redshift further, cooling toward 1 Kelvin, then 0.1 Kelvin, asymptotically approaching, but never quite reaching absolute zero. Stars will continue to form for trillions of years to come, but the rate of star formation is already declining. We've passed the peak of cosmic star formation. Gradually, as gas is consumed and not replenished, fewer and fewer stars will be born. The existing stars will age and die. Low-mass stars like red dwarfs, which can live for trillions of years, will be the last to fade. Eventually, perhaps 100 trillion years from now, the last star will wink out. The universe will enter what's called the degenerate era, dominated by dead stellar remnants, white dwarfs, neutron stars, and black holes. But even these objects aren't eternal. Black holes evaporate through Hawking radiation, a quantum process that causes them to slowly lose mass and eventually disappear in a final burst of radiation. The evaporation time depends on mass. Stellar mass black holes will take 10 to the power of 67 years to evaporate. Supermassive black holes at the centers of galaxies will take 10 to the power of 100 years or more. These timescales are almost unimaginable, but they're finite. Given enough time, even black holes will vanish. After the black holes evaporate, the universe will enter its final era, the black hole era, giving way to the dark era. By this point, perhaps 10 to the power of 100 years in the future, the universe will consist almost entirely of photons and fundamental particles like electrons and positrons, all at incredibly low temperatures, approaching but never reaching absolute zero. Structures like galaxies will have long since dispersed. The universe will be cold, dark, and approaching maximum entropy. This ultimate fate is called the heat death of the universe, though heat is a misnomer. It's really the cold death, the state of maximum entropy where no usable energy remains. Entropy, the measure of disorder, or the number of possible microstates of a system, always increases in a closed system. This is the second law of thermodynamics, one of the most fundamental principles in physics. The universe started in a low entropy state, highly ordered, all its energy concentrated in a tiny volume. As it expanded and cooled, entropy increased. Structures formed, stars ignited, life emerged, but all of this is a temporary eddy in the great flow toward maximum entropy. In the heat death scenario, temperature differences will have been erased. Everything will be at essentially the same cold temperature, just fractions above absolute zero. Without temperature gradients, no work can be done. No energy can flow. No processes can occur. Time, in a sense, will lose its meaning because nothing will change. The universe will reach a state of perfect, eternal, cold equilibrium. There's something profoundly melancholic about this vision, but also something beautiful. The universe's thermal journey is a one-way trip from order to disorder, from intense heat and energy to diffuse cold and stillness. We exist in the middle of this journey in a brief cosmic summer when stars still shine and energy still flows. The temperature of the universe right now, 2.7. Kelvin is a milestone marker on that long road from the Planck temperature to near absolute zero. But here's a thought that might offer some comfort: we don't know everything. Dark energy, which is driving the accelerated expansion, is poorly understood. There could be physics we haven't discovered yet that changes this predicted fate. Some theories propose cyclic universes, where a big crunch follows the current expansion, heating the universe back up for a new Big Bang. Others suggest quantum fluctuations might eventually nucleate new universe bubbles, even in the cold dark of the distant future. We can't see past the horizon of our current understanding. What we do know is that temperature has been the universe's constant companion throughout its history. Every major transition, every significant event, from the separation of fundamental forces to the formation of the first atoms to the ignition of the first stars, was triggered by the universe reaching specific temperatures as it cooled. Temperature isn't just a number, it's a clock marking the progress of cosmic time. When we measure the temperature of the CMB at 2.7 Kelvin, we're not just measuring how cold space is, we're measuring how old the universe is, how much it has expanded, how far it has come on its journey from heat to cold. And in a poetic sense, we're warm sparks in a cooling cosmos. Your body temperature of 310 Kelvin is vastly higher than the universe around you. Every living thing on Earth, every warm-blooded animal, every metabolically active cell is maintaining a temperature gradient against the cold of space. We're fighting entropy temporarily, creating order and warmth in small pockets powered by the energy from our sun, which itself is a temporary oasis of fusion heat in an expanding, cooling universe. As you drift towards sleep, your body temperature will drop slightly, a few tenths of a degree, as your metabolism slows. This tiny cooling mirrors the universe's grand cooling, a reminder that we're a part of these cosmic patterns. Temperature connects us to the deepest past and the furthest future. From the incomprehensible heat of the Big Bang to the ultimate cold of the heat, death temperature tells the story of existence itself, and we're living chapters in that story, brief moments of warmth in the long cool of cosmic time. But even in this mostly cold universe, there are places of extraordinary heat. stellar furnaces and cosmic violence that reach temperatures rivaling the early universe itself. And those blazing exceptions to the cosmic cold hold their own remarkable stories. Deep in the constellation, Cygnus about 6,000 light years from Earth, a star is dying in the most violent way imaginable. For just a few seconds, its core will reach 100 billion degrees, Kelvin hotter than the entire universe was just seconds after the Big Bang. In that brief moment, this single dying star will outshine entire galaxies, releasing more energy than our sun will produce in its entire 10 billion year lifetime. These stellar explosion supernovae are among the hottest natural phenomena in today's cold universe cosmic furnaces that remind us that even though the average temperature of space hovers near absolute zero, islands of extraordinary heat still blaze across the cosmos. We live in a universe of contrasts. The baseline is cold 2.7 Kelvin, barely above absolute zero. But scattered throughout this frigid expanse are pockets of intense heat places, where temperatures rival or even exceed those of the early universe. Understanding these hotspots reveals something profound about the nature of energy, the life cycles of stars, and the forging of the elements that make up everything we know, including ourselves. Let's start with the most familiar hotspot, our own sun. At its surface, the temperature is about 5,800 Kelvin, hot enough to melt any known material, but the surface is cool compared to what lies beneath. As you descend toward the core, temperature and pressure both increase. At the sun's center, where nuclear fusion occurs, the temperature reaches approximately 15 million Kelvin. At these temperatures, hydrogen nuclei have enough kinetic energy to overcome their electromagnetic repulsion and fuse together, forming helium and releasing enormous amounts of energy in the process. This fusion is what makes the sun shine, what provides the energy that powers all life on Earth. But let's put this in perspective. The sun's core at 15 million Kelvin is hot by any everyday standard. Yet, compared to the early universe temperatures we discussed earlier, it's almost cool. The universe was hotter than the sun's core for the first 10 seconds of its existence. Every point in space was once hotter than the center of our sun. The sun's fusion is merely a local recreation of processes that once occurred everywhere. Different stars burn at different temperatures, and this affects everything about them: their color, their luminosity, their lifespan. Small red dwarf stars, with masses less than half that of our sun, have core temperatures around 7 million Kelvin. They burn slowly and live for trillions of years. Massive blue giants with 10 or 20 times the sun's mass have core temperatures exceeding 30 million Kelvin. They burn through their fuel rapidly, living only a few million years before dying catastrophically. But stellar cores during normal fusion, even in the most massive stars, aren't the hottest places in the modern universe. That distinction belongs to the violent deaths of stars and the exotic objects left behind. When a massive star exhausts its nuclear fuel, its core collapses catastrophically in a fraction of a second. The collapse releases gravitational potential energy on an almost unimaginable scale, heating the core to temperatures of 100 billion Kelvin or more. This is a supernova, and for a brief moment, the collapsing core is hotter than the entire universe was during Big Bang nucleosynthesis. Let me walk you through what happens during a core collapse supernova, because the temperature progression is remarkable. Imagine a star 20 times the mass of our sun, nearing the end of its life. It's already fused hydrogen into helium, into carbon and oxygen, and continued up the periodic table, creating an onion-like structure with different elements burning in concentric shells. The core is iron, the endpoint of fusion. You can't extract energy by fusing iron. Doing so requires energy rather than releasing it. The iron core is supported only by electron degeneracy pressure, a quantum mechanical effect. When the iron core reaches about 1.4 solar masses, electron degeneracy pressure can no longer support it. In less than a second, the core collapses from roughly the size of Earth to a sphere only 20 kilometers across. The density becomes so extreme that electrons are forced into protons, creating neutrons and neutrinos in a process called neutronization. The temperature during this collapse spikes to 100 billion Kelvin or higher. At these temperatures, photons have so much energy they can split atomic nuclei apart, reversing all the fusion that occurred over the star's lifetime. The collapse halts when the core reaches nuclear density about 10 to the power of 14 grams per cubic centimeter. At this density, neutrons themselves become degenerate, providing a pressure that stops the collapse. But the infalling outer layers don't know the core has stopped. They slam into the rigid core and bounce, creating a shock wave that propagates outward. This shock wave, carrying the incredible thermal energy from the collapse, blasts through the star's outer layers, heating them to billions of degrees and ejecting them into space at a significant fraction of the speed of light. The supernova outburst visible from Earth as a star suddenly brightening by a factor of billions lasts for weeks or months. But the peak temperatures, those 100 billion Kelvin conditions in the collapsing core, last only seconds. In those brief seconds, the extreme temperatures and densities create elements heavier than iron through rapid neutron capture the R process. Gold, platinum, uranium, all the heaviest elements in the periodic table, are forged in these moments of extreme heat during stellar death. The gold in any jewelry you might wear was created in a supernova explosion, in conditions of temperature and pressure we can barely simulate even in our most powerful particle accelerators. Speaking of which, let's talk about the hottest temperatures humans have ever created, because we've actually exceeded the temperatures found in stellar cores. At CERN's Large Hadron Collider in Geneva, Switzerland physicists smash heavy ions together at nearly the speed of light. These collisions occurring in a space smaller than an atomic nucleus create temperatures of about 5.5 trillion Kelvin. That's more than 100,000 times hotter than the center of the sun. It's hotter than any naturally occurring process in the universe today, except perhaps the most energetic cosmic rays colliding with particles in space. Why create such extreme temperatures? Because at 5.5 trillion Kelvin matter undergoes a phase transition. Protons and neutrons, normally bound together by the strong force, melt into their constituent quarks and gluons, creating what's called a quark-gluon plasma. This is the state matter was in during the first microseconds after the Big Bang, before quarks combined into hadrons. By recreating these temperatures in the laboratory, physicists are literally reproducing conditions from the early universe, studying the phase transitions we discussed in the previous section, not through cosmological observation, but through direct experiment. The fact that we can create temperatures in a laboratory hotter than anything found naturally in stars is remarkable. It speaks to the power of concentrated energy. The LHC focuses enormous amounts of energy into incredibly tiny volumes, much smaller than a stellar core. Temperature, remember, is average kinetic energy. By accelerating particles to near light speed and colliding them, we give them kinetic energies that translate to temperatures exceeding those in stellar cores, even though the total energy involved is modest. It's all about energy density. Now, let's turn to neutron stars, because these objects represent another class of extreme heat in a cold universe. A neutron star is the collapsed core left behind after a supernova, a sphere about 20 kilometers in diameter, but containing more mass than the sun. When neutron stars first form, they're extraordinarily hot, with surface temperatures around 1 million Kelvin and interior temperatures possibly exceeding 1 trillion Kelvin. Over time, they cool by radiating neutrinos and photons. But even ancient neutron stars, millions of years old, maintain surface temperatures around 100,000 Kelvin, about 20 times hotter than the sun's surface. The interior of a neutron star is one of the strangest and hottest environments in nature. Densities are so extreme that atomic nuclei merge into a continuous nuclear matter. Further, neutrons might break down into their quark constituents. Some theories predict that the cores of the most massive neutron stars contain quark matter, or even stranger forms of matter we can only speculate about. The temperatures in these cores, while lower than at the moment of formation, are still measured in hundreds of billions of Kelvin. But even neutron stars aren't the most extreme compact objects. That honor belongs to black holes, or more precisely, the regions immediately surrounding black holes. Black holes themselves don't have a temperature in the conventional sense, at least not until we consider Hawking radiation, which causes them to emit thermal radiation, with a temperature inversely proportional to their mass. For stellar mass black holes, this Hawking temperature is minuscule, a tiny fraction of a Kelvin. But the accretion disks around black holes, where matter spirals inward before crossing the event horizon, are among the hottest observable structures in the universe. Matter falling toward a black hole accelerates to a significant fraction of the speed of light. Friction in the accretion disk converts this kinetic energy into heat. The inner regions of the disk closest to the black hole reach temperatures of 10 million Kelvin or higher. This is hot enough to emit X-rays and even gamma rays. When we observe X-ray binary systems where a black hole is pulling matter from a companion star, we're seeing this accretion disk plasma glowing at millions of degrees. Quasars take this to an even greater extreme. A quasar is a supermassive black hole at the center of a galaxy, millions or billions of times the mass of the Sun, actively accreting enormous amounts of matter. The accretion disk of a quasar can be light years across, and its inner regions reach temperatures exceeding 100 million Kelvin. The total energy output of a quasar can be 1 trillion times that of the Sun, making them the brightest persistent objects in the universe. We observe quasars from billions of light years away, their light red-shifted by cosmic expansion. But when that light was emitted, it came from regions hotter than almost anything else in the modern universe. Quasar jets add another dimension to this extreme heat. Many quasars and active galactic nuclei produce jets narrow beams of plasma ejected from the vicinity of the black hole at nearly the speed of light. These jets can extend for hundreds of thousands of light years, punching through their host galaxies and into intergalactic space. The particles in these jets have been accelerated to such extreme velocities that their kinetic energy corresponds to temperatures of billions or even trillions of Kelvin. When these jets collide with surrounding gas, they create shock waves that heat the gas to X-ray emitting temperatures. Here's something that might surprise you. Gamma ray bursts, the most energetic explosions in the universe after the Big Bang itself, create conditions even more extreme than supernovae. Gamma ray bursts occur during the collapse of extremely massive stars or the merger of two neutron stars. For a few seconds, they release more energy than the Sun will emit over its entire lifetime, focused into narrow jets. The temperatures in these jets during the brief moment of the burst can exceed 1 trillion Kelvin. The gamma rays produced are so energetic that if a gamma ray burst occurred within a few thousand light years of Earth and pointed at us, it could damage our atmosphere and potentially cause a mass extinction. The discovery of gamma ray bursts has a fascinating history. In the 1960s, the United States launched the Vela satellites to monitor compliance with the Nuclear Test Ban Treaty. These satellites carried detectors designed to spot the gamma ray signatures of nuclear explosions. What they found instead were bursts of gamma rays coming from space, not from Earth or even the solar system. For years, these detections were classified. When they were finally declassified in 1973, astronomers were baffled. What could produce such intense bursts of gamma rays? The mystery wasn't solved until the 1990s when better observations revealed that gamma ray bursts came from distant galaxies, meaning they had to be unimaginably energetic to be visible from such distances. Now, let's consider the contrast between these hot spots and the cold universe around them. The Sun's core is 15 million Kelvin, but just 700,000 kilometers away. At the photosphere, the temperature is only 5,800 Kelvin. A few million kilometers further out in interplanetary space, the effective temperature drops to that of the cosmic microwave background, 2.7 Kelvin. The temperature gradient is astonishing, from 15 million degrees to 2.7 degrees in less distance than the orbit of Mercury. This illustrates something fundamental. Heat naturally flows from hot to cold, spreading out and dissipating. It's the second law of thermodynamics in action. Hot spots like stars radiate their heat into the surrounding cold space. Over time, if no new energy is added, everything equalizes at a cold temperature. This is why the universe is cooling. The hot spots, the stars and galaxies, are slowly radiating their energy away. Eventually, when the last stars die and the last black holes evaporate, there will be no more hot spots. The entire universe will be cold and dark. But for now, in this era of the universe's history, these hotspots are crucial. They're where interesting things happen. Nuclear fusion in stellar cores creates the elements. Supernova explosions distribute those elements into space, seeding the interstellar medium with the raw materials for planets and life. Black hole accretion powers quasars and active galactic nuclei, which influence the evolution of entire galaxies. Without these hotspots, the universe would be a dull place, a uniform cold gas slowly expanding and cooling. The temperature contrasts, the hot islands in a cold sea, are what make the universe dynamic and interesting. There's also a philosophical point here about order and entropy. Hotspots represent local decreases in entropy regions where energy is concentrated rather than spread out. Stars are ordered structures, fighting against the tendency toward disorder. They maintain steep temperature gradients between their cores and surroundings. They convert the potential energy stored in hydrogen into radiation, creating order in the form of heavier elements. But this local ordering is paid for by an increase in total entropy. The radiation a star emits into space increases the universe's total entropy. More than the ordered structure of the star decreases it. This is the fundamental pattern of existence in our universe. Local order, local hotspots are possible only because they're embedded in a larger context of increasing disorder and cooling. Life itself is a hotspot of sorts, a local ordering of matter that maintains itself by increasing the total entropy of its environment. Your body temperature, 310 Kelvin, is maintained by metabolic processes that ultimately generate more heat and disorder than the order they create in your body. You're a small hotspot in a cold universe maintained by the energy flowing from the sun, which is itself a temporary hotspot in the cosmic cold. As you rest tonight, consider the vast temperature landscape of the cosmos. Most of space is nearly as cold as it's possible to be, hovering just above absolute zero. But scattered throughout are these extraordinary islands of heat-burning stars and exploding supernovae, accretion disks, and quasar jets, each one defying the cosmic cold for a brief moment of cosmic time. These hotspots are where the action is, where elements are forged, where energy flows, where complexity emerges. And the coldest spots make these hotspots possible. Without the cold of space as a heat sink, stars couldn't radiate and would overheat. The universe needs both extremes, the near absolute zero cold and the billion-degree heat, playing against each other in a cosmic dance that has lasted for billions of years and will continue for billions more. But creating extreme cold on Earth requires ingenuity that rivals the natural processes that create extreme heat, and humanity's quest to reach the coldest possible temperatures has yielded technologies that now shape our modern world. In a laboratory at MIT in 1995, physicists achieved something that had never occurred naturally anywhere in the 13.8 billion year history of the universe. They cooled a cloud of rubidium atoms to 170 nanokelvin, that's 0.000000017 degrees above absolute zero. At that temperature, the atoms stop behaving as individual particles and merge into a single quantum entity called a Bose-Einstein condensate, a new state of matter predicted by Einstein 70 years earlier, but never observed until that moment. These scientists had created something colder than the darkest void between galaxies, colder than the Boomerang Nebula, colder than any natural place in the cosmos. They had beaten the universe at its own game. This achievement wasn't just a scientific curiosity. The technologies developed to reach extreme cold have revolutionized medicine, computing, astronomy, and our fundamental understanding of quantum mechanics. The quest to approach absolute zero has taken us on a journey through the laws of thermodynamics, forced us to develop entirely new refrigeration techniques, and ultimately given us tools that are now essential to modern life. The story of extreme cold technology begins in the 19th century with the race to liquefy gases. At room temperature and normal pressure, gases like oxygen, nitrogen, and hydrogen exist as invisible vapors. But scientists knew that if you cooled them enough, they should condense into liquids just as water vapor condenses into liquid water. The question was, how cold, and could we reach those temperatures? This wasn't just academic curiosity. Liquefying gases would prove that they were governed by the same physical laws as other substances, and would provide a way to study matter at extreme conditions. The first major success came in 1877, when Louis-Paul Cailletet in France and Raoul Pictet in Switzerland independently liquefied oxygen at -183 degrees Celsius. They used a clever technique: compress the gas to high pressure, then allow it to expand rapidly. The expansion does work against the pressure, and this work comes from the gas's internal thermal energy, cooling it dramatically. It's the same principle we saw in the Boomerang Nebula, but now engineered and controlled in a laboratory. Nitrogen followed, quickly liquefied at -196 degrees Celsius. These early successes use cascade refrigeration, where you cool one refrigerant, use it to cool another refrigerant with a lower boiling point, and repeat the process in stages cascading down to lower and lower temperatures. But there was one gas that resisted every attempt: helium. Helium, discovered in the sun's spectrum in 1868 and isolated on Earth in 1895, has the lowest boiling point of any element. It stubbornly remained gaseous no matter what temperature researchers could achieve. Enter Heike Kamerlinghe Onnes, the Dutch physicist we met earlier. Onnes was obsessed with low temperatures. He built an elaborate cryogenic laboratory at Leiden University, complete with custom-designed equipment and a whole team of glassblowers, machinists, and technicians. His laboratory became the world center for low-temperature physics. On July 10, 1908, after years of preparation and multiple failed attempts, Onnes finally succeeded in liquefying helium at 4.2 Kelvin, just over 4 degrees above absolute zero. Onnes described watching the helium liquefy as one of the most beautiful moments of his scientific career. For hours, the gas seemed to resist remaining stubbornly vapor. Then suddenly, the characteristic shimmering of liquid appeared at the bottom of his apparatus. He had reached a temperature lower than any achieved before, opening up an entirely new realm of physics to exploration. This achievement earned him the Nobel Prize in Physics in 1913. But Onnes didn't stop there. He wondered, could he go even colder? Helium boils at 4.2 Kelvin under normal pressure. But Onnes knew that reducing the pressure above a liquid lowers its boiling point, a process called evaporative cooling. It's why sweat cools your skin. The most energetic water molecules evaporate, taking their kinetic energy with them and lowering the average temperature of what remains. Onnes applied this to liquid helium, using vacuum pumps to reduce the pressure and allowing the helium to evaporate, cooling the remaining liquid. By 1922, his laboratory had reached 1.5 Kelvin. He was now just over 1 degree above absolute zero. At these extreme temperatures, Onnes discovered something completely unexpected. In 1911, while studying the electrical resistance of mercury at liquid helium temperatures, he found that below 4.2 Kelvin, mercury's resistance didn't just decrease, it vanished entirely. He could run a current through a mercury loop, remove the power source, and the current would continue flowing indefinitely without any resistance. He had discovered superconductivity, a phenomenon that would revolutionize technology and challenge physicists' understanding of matter for decades. Superconductivity is a quantum phenomenon that only occurs at very low temperatures. When certain materials are cooled below a critical temperature, their electrical resistance drops to exactly zero. Electrons pair up in a special way and move through the material as a coherent quantum wave, unable to scatter off imperfections or lose energy to heat. This isn't just very low resistance, it's zero resistance perfect conductivity. A current in a superconducting loop could theoretically flow forever without any power source, limited only by the lifetime of the material itself. The discovery of superconductivity opened up applications that seemed like science fiction. Superconducting magnets can produce much stronger magnetic fields than conventional electromagnets, and they do so without consuming power continuously. Today, every MRI machine in every hospital uses superconducting magnets cooled by liquid helium. The Large Hadron Collider, the world's most powerful particle accelerator, uses thousands of superconducting magnets cooled to 1.9 Kelvin to steer particle beams around its 27-kilometer ring. Maglev trains in some countries use superconducting magnets to levitate above their tracks, eliminating friction. But reaching temperatures below 1 Kelvin required entirely new techniques. Evaporative cooling of helium 4 hits a wall around 1 Kelvin. To go further, physicists turn to helium-3, a lighter isotope of helium. Helium-3 remains liquid down to much lower temperatures, and dilution refrigerators invented in the early 1960s can reach temperatures around 2 millikelvin by exploiting the heat absorbed when helium-3 dissolves in helium-4. These refrigerators are now standard equipment in low-temperature physics laboratories worldwide. Going even colder requires abandoning traditional refrigeration entirely. In the 1980s and 1990s, physicists developed laser cooling, a technique that seems almost magical. The idea is to use laser light to slow down atoms. When an atom absorbs a photon from a laser beam, it gets a tiny kick in the direction the light was traveling. If you shine lasers from 6 directions, all tuned to a frequency slightly below what the atom normally absorbs, the atom preferentially absorbs photons when it's moving toward a laser beam due to the Doppler shift. Each absorption slows the atom slightly. Over millions of absorption cycles, the atoms slow dramatically, and slower motion means lower temperature. Laser cooling can reduce the temperature of a gas to around 1 microkelvin, 1/1,000,000th of a degree above absolute zero. This is cold enough that atoms move at just a few centimeters per second, slower than a crawling baby. At these temperatures, quantum effects become dominant. The atom's wave nature, normally masked by thermal motion, becomes observable. This is the realm where Bose-Einstein condensates form. A Bose-Einstein condensate, or BEC, is predicted by quantum statistics for particles called bosons. At very low temperatures, a large fraction of bosons can occupy the same quantum state, effectively becoming a single quantum entity. It's as if 1,000 atoms merge into one superatom, all described by the same quantum wave function. Einstein predicted this in 1924 based on work by Indian physicist Satyendra Nath Bose. But most physicists thought it was a mathematical curiosity that would never be observed in reality. The temperatures required seemed impossibly low. But in 1995, at the Joint Institute for Laboratory Astrophysics in Colorado, Eric Cornell and Carl Wyman successfully created the first Bose-Einstein condensate using rubidium atoms, cooled to 170 nanokelvin. A few months later, Wolfgang Ketterle at MIT created a condensate with sodium atoms. These achievements earned the 3 physicists the Nobel Prize in 2001 and opened up an entirely new field of research: ultra-cold atomic physics. Bose-Einstein condensates behave in ways that seem impossible for normal matter. They flow without viscosity like superfluids. They can be made to rotate, forming quantum vortices where the circulation is quantized, only certain specific values are allowed. They can be used to create atom lasers, coherent beams of matter, waves analogous to the coherent light of an optical laser. They're extraordinarily sensitive to magnetic and gravitational fields, making them useful for precision measurements. Now, let's talk about why we're pursuing these extreme temperatures. It's not just for the sake of records or because we can. Extreme cold is a tool, perhaps the most powerful tool we have for studying quantum mechanics and developing quantum technologies. At room temperature, thermal noise overwhelms quantum effects. Particles jiggle and vibrate so much that their delicate quantum properties are masked. But at nanokelvin temperatures, thermal noise becomes negligible, and quantum behavior dominates. This matters enormously for quantum computing. A quantum computer exploits superposition and entanglement quantum phenomena, where particles exist in multiple states simultaneously and become correlated in ways impossible for classical particles. But these quantum states are fragile, easily disrupted by thermal fluctuations. Most quantum computers must be cooled to millikelvin temperatures using dilution refrigerators to function. The coldest temperatures in the universe achieved in laboratories on Earth are essential for building the computers of the future. There's a beautiful irony here. To build more powerful computers, we need to make them colder. The history of computing has been about making processors faster, smaller, more powerful. But there's a limit to that approach, both physical and thermal. Quantum computers sidestep those limits by operating on fundamentally different principles, but they require us to master extreme cold. The future of computation may depend on our ability to create and maintain temperatures colder than outer space. The James Webb Space Telescope provides another dramatic example of extreme cold technology in action. Webb's instruments must operate at incredibly low temperatures to detect faint infrared radiation from distant galaxies. One of its instruments, the mid-infrared instrument, or MIRI, is cooled to 7 Kelvin using a complex system involving the telescope's sun shield and passive radiators. But 7 Kelvin isn't cold enough for some of MIRI's detectors. They need to be at 6 Kelvin, requiring an active cryocooler, a mechanical refrigerator operating in space. This cryocooler is an engineering marvel. It uses helium gas compressed and expanded in a cycle to remove heat, gradually cooling MIRI's detectors to their operating temperature. Maintaining 6 Kelvin in space with the sun heating one side of the telescope and the cold of space on the other is an extraordinary feat of thermal engineering. It's taken decades of research and development to make such systems reliable enough for a multi-billion-dollar space mission that can't be repaired once launched. The coldest place in the universe right now is probably not in space at all. It's in a laboratory somewhere on Earth, perhaps at MIT or Stanford or one of the national laboratories where physicists are cooling atoms to nanokelvin temperatures. We've created conditions colder than the cosmic microwave background, colder than the Boomerang Nebula, colder than anything nature has produced in 13.8 billion years. That's a remarkable testament to human ingenuity and our drive to explore the limits of physical reality. But achieving extreme cold isn't easy, and it's not cheap. A dilution refrigerator costs hundreds of thousands of dollars and requires constant maintenance. Liquid helium, essential for most ultra-low temperature research, is becoming scarcer and more expensive as the world's helium reserves deplete. Helium is a non-renewable resource on Earth. Once released into the atmosphere, it eventually escapes into space. There are ongoing efforts to recycle helium and develop closed-cycle cooling systems, but the resource constraints are real. This raises a question: is it worth it? Should we be spending resources to create places colder than outer space? The answer from both a scientific and practical perspective is overwhelmingly yes. The technologies developed in the pursuit of extreme cold have given us MRI machines that save lives, superconducting magnets that enable particle physics research, quantum computers that may revolutionize computing, and space telescopes that reveal the universe's deepest secrets. The investment in cryogenic technology has paid dividends far beyond the original research goals. There's also something profound about the human impulse to explore extremes. We've climbed the highest mountains, Dove, to the deepest ocean trenches, ventured into space, and created the hottest and coldest temperatures possible. We're a curious species driven to test the limits of what's possible. The quest for absolute zero is part of that larger quest to understand our universe completely, to probe every regime of physics, to see what happens at the boundaries. And we've learned that absolute zero is indeed unreachable, not because of limitations in our technology, but because of fundamental physics. The third law of thermodynamics tells us that we cannot reach absolute zero through any finite series of processes. Each step closer requires exponentially more effort. We can get to 170 nanokelvin, perhaps eventually to picokelvin or even femtokelvin. But that final gap to absolute zero remains forever unbridgeable. There's something almost poetic about that. The universe has limits, boundaries that cannot be crossed no matter how advanced our technology becomes. Absolute zero is one such boundary. The speed of light is another. These limits aren't failures. They're features of reality telling us something deep about the structure of space-time and the nature of matter and energy. Learning to work within these limits, to approach them asymptotically, but accept that we'll never quite reach them, is part of what it means to do science. As you drift towards sleep, think about the scientists in their laboratories working through the night to cool atoms to a billionth of a degree above absolute zero. They're creating the coldest places in the universe, tiny pockets of extreme cold sustained by sophisticated technology, isolated from the room temperature world by elaborate thermal shields and vacuum chambers. These efforts represent humanity's attempt to master one of nature's fundamental parameters: temperature. From the cosmic heat of the Big Bang to the engineered cold of a quantum computer, temperature has been our guide through physics, and our ability to control it has shaped our civilization. But understanding extreme cold in laboratories is one thing. Understanding how temperature shapes the possibility of life across the cosmos is quite another. And that question leads us to consider the delicate thermal balance required for existence itself. 4 billion miles from the sun, where sunlight is 1,000 times dimmer than on Earth, and surface temperatures plunge to minus 180 degrees Celsius. Something extraordinary may be happening. Beneath the icy crust of Europa, one of Jupiter's moons, there exists an ocean of liquid water, kept warm by tidal heating from Jupiter's immense gravity. In that dark, cold ocean, far from any sunlight, some scientists believe life might exist. Not life as we typically imagine it, but life adapted to extreme cold, surviving in conditions that would kill any Earth organism in seconds. This possibility challenges everything we thought we knew about the relationship between temperature and life, and it forces us to reconsider what habitable really means. Temperature isn't just one factor among many for life. It's perhaps the most fundamental constraint. Too hot and the complex molecules necessary for biology break apart. Too cold and chemical reactions slow to a standstill. Life, as we know it, exists within a relatively narrow temperature range. But, as we know it, is an important qualifier. The universe may harbor forms of life adapted to temperatures we consider impossibly extreme, and understanding the relationship between temperature and habitability is crucial as we search for life beyond Earth. Let's start with what we know Earth's habitable temperature range. The vast majority of life on our planet exists between about minus 20 degrees Celsius and 120 degrees Celsius. This isn't arbitrary. These limits are set by the chemistry of water and carbon-based molecules. Water freezes at 0 degrees Celsius under standard pressure, and ice crystals can rupture cell membranes. Most proteins denature, losing their functional shape above about 60 degrees Celsius. These chemical constraints define what biologists call the habitable zone for Earth-like life. But Earth hosts remarkable exceptions that push these boundaries. In Antarctica's dry valleys, psychrophiles, cold-loving microorganisms live in temperatures as low as minus 25 degrees Celsius. These organisms produce antifreeze proteins that prevent ice crystal formation in their cells. Their enzymes are specially adapted to function at low temperatures, flexible, where normal enzymes would be rigid. Some can metabolize so slowly that they divide perhaps once per century, essentially hibernating through the coldest periods and becoming active during brief warming events. At the other extreme, hyperthermophils thrive in deep-sea hydrothermal vents at temperatures exceeding 120 degrees Celsius. The current record holder, Methanopyrus candleri, can grow at 122 degrees Celsius. These organisms have heat-stable proteins, reinforced cell membranes, and molecular repair mechanisms that fix damage from thermal stress. They represent the hot edge of life's temperature tolerance, and they show us that biology can adapt to conditions that seem hostile to existence. These extremophiles are more than curiosities. They fundamentally changed how we think about habitability. Before their discovery, scientists assumed life required moderate temperatures, Earth-like conditions. The discovery of thriving ecosystems around hydrothermal vents in 1977 shattered that assumption. Life doesn't need sunlight. It doesn't need moderate temperatures. It needs energy, liquid water, and the right chemical ingredients. Temperature constrains where those conditions exist, but the range of tolerable temperatures is much wider than we once thought. This realization revolutionized the search for extraterrestrial life. Before extremophiles, scientists focused on planets in the narrow Goldilocks zone, where temperatures allow liquid water on the surface. Earth is in this zone around our sun, not too hot, not too cold, but just right. Venus, closer to the sun, is too hot at surface at 460 degrees Celsius, hot enough to melt lead. Mars, further out, is too cold, averaging minus 60 degrees Celsius, with any surface water frozen solid. Earth occupies the sweet spot. But extremophiles taught us that life might exist outside this traditional habitable zone in places we'd overlooked. Icy moons with subsurface oceans became prime targets. Europa, orbiting Jupiter, has a surface temperature of minus 160 degrees Celsius, far outside the sun's habitable zone. But tidal heating from Jupiter's gravity generates enough internal heat to maintain a liquid ocean beneath the ice. That ocean might have existed for billions of years, potentially giving life time to arise and evolve in conditions of stable extreme cold. Enceladus, a small moon of Saturn, tells a similar story. The Cassini spacecraft detected geysers erupting from Enceladus's south pole, shooting water vapor and ice particles into space. Analysis revealed that these geysers originate from a subsurface ocean, and the water contains organic molecules, hydrogen, and salts. These are ingredients for life. The temperature of Enceladus's ocean is estimated at around 0 degrees Celsius near the ice shell, potentially warmer near the rocky core. Could life exist in those frigid depths? We don't know, but the possibility is tantalizing. Let's consider what cold does to the chemistry of life. At Earth, temperature's chemical reactions proceed at rates suitable for biology. Enzymes catalyze reactions. DNA replicates, proteins fold. But as temperature drops, molecular motion slows. Reaction rates decrease exponentially, with temperature following the Arrhenius equation. At 0 degrees Celsius, many biological reactions are 10 times slower than at 37 degrees Celsius. At minus 20 degrees, they're perhaps 100 times slower. This presents a challenge for life in cold environments. Slow metabolism means slow growth, slow reproduction, slow response to environmental changes. But it's not impossible. Psychrophiles cope by producing enzymes that are more flexible and active at low temperatures. Their cell membranes remain fluid by incorporating unsaturated fatty acids that don't solidify in cold. They produce antifreeze compounds that prevent ice formation. These adaptations allow life to continue, albeit slowly, at temperatures where we'd expect biochemistry to grind to a halt. There's also an energetic consideration. Life requires energy typically from chemical reactions or from light. In cold environments far from the sun, photosynthesis isn't an option. Life must rely on chemosynthesis deriving energy from chemical gradients such as those at hydrothermal vents. On Europa or Enceladus, any life would likely be chemosynthetic, perhaps feeding on hydrogen and carbon dioxide, producing methane similar to methanogens on Earth. These are slow, energy-poor ecosystems, but they could be stable over geological timescales. Now let's talk about the concept of the habitable zone in more depth, because it's more nuanced than often portrayed. The traditional habitable zone is defined by the distance from a star where liquid water can exist on a planet's surface. For our Sun, this zone extends from about 0.95 to 1.37 astronomical units, with Earth sitting comfortably at 1 astronomical unit. Planets within this zone receive enough stellar radiation to keep their surfaces above freezing, but not so much that water evaporates. But this definition has limitations. It assumes an Earth-like atmosphere and geology. A planet closer to its star could maintain liquid water if it has a thin atmosphere that limits the greenhouse effect. A planet further out could have liquid water with a thick atmosphere rich in greenhouse gases. Venus, for instance, should theoretically be in the habitable zone, but its dense carbon dioxide atmosphere has created a runaway greenhouse effect, making the surface uninhabitable. Mars presents the opposite problem. It's near the outer edge of the habitable zone, but it has a thin atmosphere that can't retain heat. Water exists on Mars, but it's frozen in polar caps and subsurface ice. However, Mars may have been warmer and wetter in the past, with liquid water flowing on its surface billions of years ago. If so, life might have arisen during that warmer period and potentially survived in subsurface refuges, where liquid water might still exist. This brings us to the concept of subsurface habitability. Many bodies in the solar system, including Mars Europa and Enceladus, might have habitable environments beneath their surfaces insulated from the cold vacuum of space. On Earth, life exists several kilometers underground in aquifers and rock fractures, fed by geothermal heat and chemical energy from minerals. Similar subsurface biospheres could exist throughout the solar system, hidden from view, but potentially teeming with microbial life. The discovery of such life would profoundly change our understanding of habitability and our estimates of how common life might be in the universe. If life can thrive in subsurface oceans on icy moons, then countless worlds throughout the galaxy might harbor life even if their surfaces are frozen wastelands. The habitable zone expands dramatically when we consider subsurface environments. Let's consider Titan-Saturn's largest moon because it represents an entirely different kind of cold environment. Titan's surface temperature is minus 179 degrees Celsius, cold enough that water ice is as hard as rock and methane exists as a liquid. Titan has lakes and seas not of water, but of liquid methane and ethane. It has a thick nitrogen atmosphere, clouds, and even rain, but the rain is liquid methane. It's a world where the familiar processes of Earth precipitation, erosion, evaporation occur with completely different chemistry. Could life exist on Titan? Not life as we know it. Water-based biochemistry would be frozen solid at those temperatures. But some scientists have speculated about life based on liquid methane instead of water with different chemistry operating at cryogenic temperatures. This is highly speculative, and we have no evidence such life exists. But Titan forces us to think creatively about what life might look like under radically different temperature regimes. The Cassini mission studied Titan for 13 years and found something puzzling. The atmosphere contains less hydrogen than expected, and acetylene, a compound abundant on the surface, is less common than models predict. Some scientists suggested these discrepancies could indicate metabolism, organisms consuming hydrogen and acetylene for energy. But non-biological explanations are also possible, and we'd need direct sampling to know for sure. The point is that even at minus 179 degrees Celsius, we can't rule out the possibility of life, just a very alien form of it. Temperature also affects habitability through its influence on planetary atmospheres. A planet's surface temperature determined by its distance from its star and its atmospheric composition affects how much water vapor can exist in the atmosphere. Water vapor is a greenhouse gas, so more water vapor means more warming, which allows even more water vapor, a positive feedback loop. This is partly why Venus, which started with more solar heating than Earth, experienced a runaway greenhouse effect. Conversely, on a cold planet, water vapor condenses out of the atmosphere. With less greenhouse warming, the planet cools further, potentially entering a runaway icehouse effect. Earth has skirted this edge multiple times during snowball Earth events in the deep past, when the entire planet may have been covered in ice. Life survived these episodes, but they were close calls demonstrating how delicate the temperature balance is for maintaining habitability. Exoplanet discoveries over the past 3 decades have given us thousands of worlds to study, and we're beginning to understand the diversity of planetary temperatures and environments. Some exoplanets, called hot Jupiters, orbit so close to their stars that their atmospheres are stripped away, and their surfaces can reach 2,000 Kelvin or more. Others, rogue planets ejected from their star systems, drift through interstellar space at temperatures barely above the cosmic microwave background. And in between are planets in habitable zones, some potentially with liquid water and temperatures suitable for life. One particularly intriguing discovery is TRAPPIST-1, a system of 7 Earth-sized planets orbiting a cool red dwarf star. 3 of these planets, TRAPPIST-1 E, F, and G, are in the habitable zone where liquid water could exist. But red dwarf stars are much cooler than the Sun, so their habitable zones are much closer in. These planets are tidally locked, always showing the same face to their star, creating extreme temperature differences between the day and night sides. Could life adapt to such conditions, perhaps migrating around the planet to stay in a habitable temperature zone, or existing in the twilight band between the frozen night side and scorching day side? We don't know yet, but these questions highlight how temperature is just one piece of the habitability puzzle. Atmospheric circulation can redistribute heat-moderating temperature extremes. Oceans can store and transport thermal energy. Greenhouse gases can warm a cold planet. Ice and snow can reflect sunlight, cooling a warm planet. Habitability emerges from the complex interplay of all these factors, with temperature as a central but not sole determinant. There's also the question of whether life needs to be continuous, or can it survive in a dormant state during periods of extreme cold? On Earth, many organisms can enter cryptobiosis, a state of suspended animation, where metabolic activity essentially stops. Tardigrades, microscopic animals, can survive temperatures from near absolute zero to over 150 degrees Celsius when desiccated. Bacterial spores can remain viable for thousands or even millions of years. If life on Mars existed during a warmer past, could it persist in a dormant state, in subsurface ice, waiting for conditions to improve? This idea of dormant life surviving through unfavorable periods opens up the possibility of panspermia life spreading between worlds. If microbial life can survive the cold of space and the radiation exposure during a journey of millions of years, then impacts could transfer life between planets or even between star systems. The cold of space, rather than being a barrier to life, might actually preserve organisms in stasis, allowing them to survive journeys that would otherwise be impossible. As we search for life beyond Earth, understanding temperature's role in habitability is crucial. The missions we send, the instruments we design, the places we explore, all depend on our models of where life can exist and what conditions it requires. Every discovery of life in extreme environments on Earth expands our search parameters and gives us hope that life might be more common, more resilient, and more diverse than we ever imagined. Think about this. As you rest, life on Earth maintains itself within a narrow temperature range on a planet that happens to orbit at just the right distance from a stable star. But beneath the ice of distant moons and subsurface aquifers on frozen worlds, perhaps even in exotic chemical systems, we haven't imagined life might exist at temperatures we consider impossibly hostile. The universe is cold, but life tenacious and adaptive may have found ways to thrive even in the deepest freeze. Temperature sets the stage, but biology is a remarkably inventive playwright, and the cosmic drama of life may be playing out in more theaters than we've yet discovered. These questions about life temperature and habitability ultimately lead us to something deeper. What does temperature itself mean? What has this journey through hot and cold taught us about the nature of existence, time, and our place in the vast cooling cosmos? We've traveled from the hottest moment of creation to the coldest corners of the cosmos, from laboratory experiments that beat the universe at its own game to distant moons, where life might huddle in frozen oceans. We've seen how temperature isn't just a number on a thermometer, but a fundamental thread woven through the fabric of reality itself, connecting the smallest quantum fluctuations to the grandest cosmic epochs. Now, as our journey draws to a close, it's time to ask, what does all of this mean? What does the temperature of the universe teach us about existence, about time, about ourselves? Let me start with a story that brings everything together. In 1850, a German physicist named Rudolf Clausius was studying steam engines, trying to understand why they could never be perfectly efficient. No matter how well designed, some energy was always lost as waste heat. This observation, seemingly mundane, led Clausius to formulate what became the second law of thermodynamics in any closed system. Entropy disorder always increases over time. Heat flows from hot to cold, never the reverse unless work is done. This law, born from practical engineering, turned out to describe not just steam engines, but the fate of the entire universe. Entropy, the measure of disorder or the number of ways a system's components can be arranged, is intimately connected to temperature. A hot object has high entropy because its molecules are moving randomly in countless different ways. A cold object has lower entropy because molecular motion is more constrained. The second law tells us that the universe is on a one-way journey from low entropy to high entropy, from order to disorder, from concentrated energy to diffuse equilibrium. This is why time has an arrow, why we remember the past but not the future, why eggs break but don't spontaneously reassemble. The temperature history of the universe is the story of this entropy increase playing out on the grandest scale. At the Big Bang, all the universe's energy was concentrated in an infinitesimally small space. This was a state of extraordinarily low entropy, not because it was cold, it was unimaginably hot, but because all the energy was organized, concentrated, not spread out. As the universe expanded, that energy dispersed, temperature dropped, entropy increased, and this process continues today and will continue into the far future. Think about what this means. Every star that shines, every life that lives, every thought you think, all of it is part of the universe's journey toward maximum entropy. Stars convert the concentrated nuclear energy of hydrogen into diffuse heat and light, increasing entropy. Life maintains local order by consuming energy and producing heat and waste, increasing the total entropy of its environment. Your body right now is a temporary island of order in a sea of increasing disorder, maintained only by the constant flow of energy from the food you eat, which ultimately comes from the sun, which is itself slowly converting order into disorder through fusion. This might sound depressing, the idea that everything is running down, heading toward a cold, dark, maximum entropy state. But there's beauty in it too. The universe started in a state of incredible potential, all the concentrated energy ready to do work, to create, to become. And in the process of running down, of approaching equilibrium, the universe has created everything we see: galaxies, stars, planets, life, consciousness. All the richness and complexity of existence emerge during this journey, from hot to cold, from order to disorder. The physicist Sean Carroll describes this beautifully. He points out that we live in an era when the universe has cooled enough for complex structures to form, but hasn't yet reached equilibrium. Stars still shine because there are temperature gradients, hot stellar cores, and cold space driving energy flow. Life exists because Earth has a temperature difference between the hot sun and cold space, allowing energy to flow through our biosphere. In the far future, when the universe reaches heat death, and everything is at the same cold temperature, no gradients will exist. No energy will flow. Nothing will happen. But right now, in this cosmological moment, we're in the sweet spot where interesting things can occur. Temperature gradients are what make change possible. They're what drive engines, whether mechanical engines or the biological engines of life. The hot and the cold existing side by side create the potential for work, for transformation, for existence itself. In this sense, the cold of space isn't an enemy of life or activity. It's a partner with the heat of stars, creating the contrasts that make the universe dynamic rather than static. Let's return to absolute zero, because it represents more than just the coldest possible temperature. It represents a limit, a boundary that nature has drawn. We can approach it asymptotically, getting closer and closer, but we can never reach it. This unreachability isn't a technological limitation. It's a fundamental law of physics, the third law of thermodynamics. Why does this matter philosophically? Because it tells us that perfect stillness, perfect order, perfect cold is impossible. There's always some residual motion, some quantum uncertainty, some irreducible aliveness, even at the edge of existence. The universe refuses absolute stasis. Even in the coldest possible state, quantum fluctuations persist, particles jitter with zero-point energy, and the Heisenberg uncertainty principle ensures that nothing can be completely, utterly still. In the deepest possible cold, the universe maintains a kind of fundamental restlessness. This parallels something profound about existence itself. There's no final state, no ultimate ending where everything stops completely. The universe will cool toward heat death, yes, but even then, quantum fluctuations will continue. Virtual particles will pop in and out of existence. The quantum vacuum will never be truly empty or truly still. Some physicists even speculate that, given infinite time, quantum fluctuations could eventually nucleate new universes. New Big Bangs continuing the cycle of creation from the ashes of the cold death. Now, let's talk about what we are in this context. You, me, every living thing on Earth, we're hot spots in a cold universe. Your body temperature is about 310 Kelvin more than 100 times warmer than the cosmic background. You maintain this temperature through metabolism, burning food, consuming the chemical energy stored in the bonds of molecules. This energy ultimately comes from the sun, which radiates it from fusion reactions in its core. The sun's energy comes from gravitational collapse and nuclear fusion, converting mass into energy, according to Einstein's equation, E equals mc squared. So, in a real sense, you're made of starlight, not just metaphorically because your atoms were forged in stars, but literally because the energy that powers your life, that maintains your warmth, that enables every thought and movement, is energy that flowed from the sun to Earth, to your food, to you. You're a temporary concentration of energy and order, maintaining yourself against the universe's tendency toward equilibrium, fighting the good, fight against entropy for the brief span of a human lifetime. And when you die, your body's temperature will drop toward equilibrium with your surroundings. The energy you've been concentrating will disperse. The order you've been maintaining will dissolve. In thermodynamic terms, your entropy will increase. But the atoms that made you up forged in stellar cores billions of years ago will persist. They'll cycle through other forms, other organisms eventually, perhaps back into space and into new stars. You're not just in the universe. You're of the universe, a temporary eddy in the great flow of energy and entropy, but made of the same stuff as stars and planets, participating in the same cosmic dance. There's something comforting about understanding our place in this thermal journey. We're not separate from the universe observing it from outside. We're part of it, intimately connected to its history and its future. The fact that we're warm in a cold cosmos isn't a defiance of nature, but an expression of it. Temperature gradients energy flows the journey from hot to cold. These are what make us possible. Let's think about time itself through the lens of temperature. Why does time seem to flow in only one direction? Why do we age? Why do things break and wear out? Why does entropy always increase? The answer, according to thermodynamics, is that time's arrow is defined by the direction of increasing entropy. We perceive time moving forward because we perceive entropy increasing. If entropy could decrease spontaneously, if heat could flow from cold to hot without work being done, time's arrow would reverse. The universe is cooling as time made visible. Every moment that passes, the universe expands a bit more, cools a bit more, becomes a bit more disordered. The cosmic microwave background cools from 2.7255 Kelvin to 2.7254 Kelvin over unimaginably long timescales. But that cooling is real, and it marks time's passage. Temperature isn't just correlated with time. In a deep sense, the temperature history of the universe is time, is the physical manifestation of time's flow. This brings us to perhaps the deepest question. Could the universe's thermal death be avoided or reversed? Some cosmologists have speculated about scenarios where the universe's expansion might halt and reverse, leading to a big crunch where everything reheats to Big Bang conditions. Others suggest that dark energy might change its properties over cosmic time, altering the universe's fate. And, as mentioned earlier, quantum fluctuations might, over inconceivably vast timescales, nucleate new universes even in the cold dark of heat death. But based on current observations, the most likely fate is the Big Freeze. The universe will expand forever, accelerating due to dark energy. Stars will exhaust their fuel. Galaxies will drift apart beyond each other's cosmic horizons. Black holes will evaporate through Hawking radiation. Eventually, only a thin soup of photons and fundamental particles will remain at temperatures approaching but never quite reaching absolute zero. This will take not billions or trillions of years, but 10 to the power of 100 years or more. Timescales so vast they're almost meaningless. Should this disturb us? I don't think so. The universe has already given us 13.8 billion years of structure, complexity, and wonder. Stars have formed and died in cycles enriching space with heavy elements. Planets have coalesced. Life has emerged at least once and possibly countless times. Intelligence and consciousness have arisen, allowing the universe to become aware of itself. The fact that this can't last forever doesn't diminish its value. If anything, the temporary nature of cosmic complexity makes it more precious. There's a parallel here with human life. We don't live forever. Our bodies are temporary, sustained for decades by the energy flow from metabolism, then returning to equilibrium with the environment. But the finite span of a human life doesn't make it meaningless. The experiences, relationships, thoughts, and feelings that fill those years matter because they happen, not because they last forever. The same is true of the universe's complexity. Stars matter. Life matters. Consciousness matters. Not because they're eternal, but because they exist at all in a universe that could have remained simple hot plasma expanding into cold, empty space. Let me share one final thought about the meaning of cold. Throughout this journey, we've seen that cold isn't just the absence of heat. It's a state with its own character, its own physics, its own beauty. At extreme cold, matter behaves in ways impossible at higher temperatures. Superconductivity, superfluidity, Bose-Einstein condensation. These quantum phenomena only emerge when thermal noise is quieted, when the universe is allowed to show its quantum nature undisturbed. In a sense, cold is when the universe reveals its deepest truths. The cosmic microwave background at 2.7. Kelvin is cold, but it's also the most informative thing we can observe, carrying details about the universe's composition, age, and geometry. The coldest laboratory experiments reveal quantum mechanics in its purest form, showing us the fundamental nature of matter and energy. Cold isn't sterile or dead. It's clarifying, stripping away the noise, and showing us what lies beneath. And space itself, cold and vast, is the canvas on which everything plays out. The cold of space makes the warmth of stars meaningful. The near absolute zero background makes every hotspot, every galaxy, every living world stand out as a beacon of energy and order. The contrast between hot and cold, between order and entropy, between the concentrated and the diffuse, this is what gives the universe its texture, its drama, its story. As you drift into sleep tonight, your body temperature will drop slightly. Your metabolism slowing, your brain activity quieting. This tiny cooling mirrors the universe's grand cooling, a reminder that you're connected to cosmic processes in intimate ways. The warmth you feel beneath your blankets is your body's rebellion against entropy, a temporary stand against equilibrium. And in the morning, when you wake, your temperature will rise again. Metabolism, increasing energy, flowing. Maintaining the improbable order that is a living human being for one more day. We've explored temperature from the Planck epoch to the heat. Death from laboratory, nano-Kelvin, to stellar cores, from the chemistry of life to the meaning of time. Throughout this journey, one theme has emerged. Temperature isn't just a physical property. It's a lens through which we can understand the universe's past, present, and future. It connects quantum mechanics to cosmology, thermodynamics to biology, physics to philosophy. The universe is cold, nearly as cold as it can possibly be. But within that cold islands of warmth persist stars, burning planets orbiting life, evolving minds thinking. We're privileged to exist during this brief cosmic summer when stars still shine and energy still flows. Someday in the unimaginably distant future, the universe will grow colder, still approaching, but never reaching absolute zero. But that's not now. Now is the time of stars of life, of consciousness. Now is when the universe looks at itself through billions of eyes and asks, why now is when temperature matters, when the contrast between hot and cold creates the conditions for wonder. Thank you for joining me on this journey through the temperature of the universe. I hope it's given you a new appreciation for the cosmic cold that surrounds us and the precious warmth we maintain against it. As you rest, remember that you're part of something vast and ancient, a universe cooling over billions of years, and yet something immediate and intimate, the warmth of your own body, the quiet rhythm of your own breath, the hot and the cold, the cosmic and the personal, all connected through the fundamental physics of temperature. Sleep well, and may your dreams be filled with the quiet wonder of stars, shining in the cold dark of quantum fluctuations, dancing at the edge of absolute zero, of the universe's long journey from fire to ice, and everything beautiful that emerged along the way. Until next time, when we'll explore another mystery of the cosmos together, rest easy knowing that even in the deepest cold, the universe has not forgotten how to burn with light, with life, with meaning. Good night.